The universe should not exist. And yet, here it is. This simple, stark fact, when held in the mind, is perhaps the most profound and unsettling mystery we can contemplate. The prevailing scientific narrative of our cosmic origins tells a story of exquisite balance and improbable fortune. In the very first moments of the universe, in the incandescent crucible of the Big Bang, matter and its mirror image, antimatter, were forged from pure energy in almost perfectly equal amounts. But matter and antimatter are mortal enemies. When they meet, they annihilate each other in a flash of pure energy, leaving behind nothing but a sea of light. If the balance had been perfect, if for every particle of matter there had been an identical particle of antimatter, the universe would have been a short-lived and sterile affair. As it cooled, a great cosmic annihilation would have occurred, leaving behind a cold, dark, and empty cosmos, filled only with a diffuse, featureless bath of radiation. There would be no stars, no galaxies, no planets, and no people to wonder at the silence. And yet we are here. We live in a universe that is overwhelmingly, almost exclusively, made of matter. This means that somehow, in that first, fiery instant, a tiny, almost imperceptible imbalance occurred. For every billion pairs of matter and antimatter particles that were created and then destroyed, a single, solitary particle of matter was left over. It is this minuscule, 1 in a billion cosmic anomaly, this sleight of hand in the universe's initial coin toss. That is the sole reason for our existence. Everything we see, from the grandest superclusters of galaxies to the very atoms that make up our bodies, is the leftover, residual matter from that great primordial annihilation. The universe we inhabit is a cosmic rounding error. This matter-antimatter asymmetry is one of the deepest and most unsolved puzzles in modern physics. What tipped the scales? What was the subtle flaw in the universe's initial symmetry that allowed matter to gain its tiny, but ultimately decisive, victory over its antimatter twin? The answer is not yet known, but it is a question that points to a deeper and more profound truth that our very existence is predicated on a series of seemingly impossible coincidences, on a universe that seems to have won a cosmic lottery of almost unimaginable odds. The universe exists. This simple three-word statement, when deeply considered, is the wellspring of all our science, all our philosophy, all our art. We find ourselves adrift in a cosmos of immense scale, of breathtaking beauty, and of intricate, and often bewildering, complexity. It is a realm of 100 billion galaxies, each a glittering city of 100 billion stars, and on at least one small, rocky planet, orbiting one unremarkable star in a quiet, suburban spiral arm of one of these galaxies. The universe has woken up. It has produced conscious beings, beings capable of turning their gaze back upon the cosmos and asking the most fundamental question of all: why is there something rather than nothing? This is the big question, a riddle that has haunted the human mind since the dawn of thought. The state of nothingness, a complete and utter absence of all that is of matter, of energy, of space, of time, of the very laws that govern them, seems, to many, to be the simpler, more natural, and more probable state. Existence, with all its intricate machinery and its seemingly arbitrary rules, seems to be the state that requires a special explanation. It is not just a philosophical musing. It is a puzzle that is deeply embedded in the very heart of our most advanced scientific theories. Our best scientific story, the Big Bang model, provides a stunningly successful narrative of how the universe has evolved over the last 13.8 billion years, from a hot, dense, and simple initial state to the cool, complex, and structured cosmos we see today. But it cannot and does not explain why. there was a universe to begin with. It does not explain the origin of the initial conditions, nor the source of the fundamental laws that allowed the story to unfold. And it is in the nature of these laws and initial conditions that the mystery deepens. The universe seems to be exquisitely and almost miraculously fine-tuned for the existence of complexity and life. The fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton appear to be set to values that fall within an incredibly narrow, life-permitting range. If the strong nuclear force, for example, the force that binds protons and neutrons together in atomic nuclei, were just a few percent weaker, then stable atoms heavier than hydrogen would not be able to form. The universe would be a monotonous and lifeless sea of hydrogen gas. If it were a few percent stronger, then all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for the long-lived stars, like our sun, that are necessary for the slow, patient evolution of life. The ratio of the strength of the electromagnetic force to the force of gravity is another, even more astonishing. Example: the number is immense, about 10 to the power of 40. If this ratio were significantly different, the universe would be a barren and sterile place. If gravity were much stronger, stars would burn out in a flash, collapsing into black holes before life could ever get started. If it were much weaker, then matter would never have been able to clump together to form the stars and galaxies in the first place. The list of such cosmic coincidences is long and growing. The mass of the electron, the expansion rate of the universe, the density of dark energy, all of these, and many more, seem to be balanced on a knife edge. The probability of all of these parameters falling, by pure chance, into the tiny, life-permitting sliver of the vast landscape of possibilities seems almost infinitesimally small. It is as if we have walked into a cosmic casino and found that a single, randomly thrown set of dice has come up with the same specific and incredibly complex winning number 1,000 times in a row. The mystery of our existence is deepened still further when we consider the nature of the vacuum, the seemingly empty space that fills the cosmos. According to the strange and beautiful laws of quantum mechanics, a true vacuum is not empty at all. It is a seething, energetic sea of virtual particles, constantly popping into and out of existence, a quantum foam that fills all of space. When physicists try to calculate the total energy density of this vacuum, they get a number that is astronomically, absurdly large. If this vacuum energy had the gravitational effect that our current theories predict, it would have caused the universe to expand at an unimaginable rate, ripping itself apart in the first fraction of a second of its existence. There would be no stable structures, no stars, no galaxies, no life. And yet, we observe that the universe is not being ripped apart. In fact, the observed energy of the vacuum, which we now associate with dark energy, is incredibly, exquisitely small, almost zero. The discrepancy between the theoretical prediction and the observed reality is a staggering 120 orders of magnitude. It is, by a wide margin, the worst prediction in the entire history of science. The fact that the vacuum energy is so tiny, that our universe is so stable, is another profound and completely unexplained cosmic coincidence. And then, there is the puzzle we began with, the asymmetry between matter and antimatter. The universe we inhabit is a universe of matter, but our best theories of the early universe predict that matter and antimatter should have been created in perfectly equal amounts. If this had been the case, they would have annihilated each other, leaving behind a cold, dark universe of pure light. The fact that we are here, that matter exists at all, is a testament to a tiny 1 in a billion imbalance that occurred in the first fiery moments of creation. The precise mechanism that produced this life-giving asymmetry remains one of the great, unsolved mysteries in all of particle physics. The question, why is there something rather than nothing, is not a question that science can yet answer. The scientific method is a powerful tool for explaining how things work, for describing the processes that unfold within a given set of rules and initial conditions. But it is not, at present, equipped to explain why those rules and conditions exist in the first place, or why there is a universe for them to apply to at all. This profound and beautiful challenge lies at the very heart of physics, of cosmology, and of philosophy, inviting us to confront the limits of our empirical knowledge and perhaps the very nature of reality itself. The question, why is there something rather than nothing, is predicated on the assumption that nothing is a simple, straightforward, and perhaps even more natural state than something. But when we try to pin down what we actually mean by nothing, the concept quickly dissolves into a series of profound and perplexing paradoxes. It is a word that is easy to say, but almost impossible to truly conceive of. In our everyday, colloquial use, nothing often refers to an empty space. If you open a box and find it empty, you might say, there's nothing in it. But an empty box is not nothing. It is a box, a container, an object that exists in space. And the space inside the box is not nothing. It is a three-dimensional volume, a part of the geometric fabric of our universe. What if we remove the box and just consider the empty space itself? Is that nothing? Not according to modern physics. Space, as we now understand it from Einstein's general theory of relativity, is not a passive, empty stage. It is a dynamic, physical entity, a space-time that can be bent, warped, and stretched by the presence of matter and energy. It is a something in its own right. So, to get to a truer nothing, we must imagine the absence of space itself. But how can we even begin to do that? Our minds are so deeply conditioned to think in spatial terms that to imagine a state devoid of space is a cognitive feat that borders on the impossible. The moment we try to picture nothing, we inevitably picture it as a kind of black, empty void, which is itself a spatial concept. This leads us to the realm of philosophy, to the idea of an absolute nothingness. This would be a state of complete and utter non-existence. No matter, no energy, no space, no time, no physical laws, no mathematical truths, no logical principles, no consciousness, no properties, no potentiality. It would not just be the absence of all things, it would be the absence of the very possibility of things. It is a concept of such radical negation that it may be, in a deep sense, logically incoherent. The very act of defining it, of giving it a name, seems to imbue it with a kind of existence. This philosophical quagmire is why physicists, when they speak of a universe from nothing, are almost always speaking of a very different and much more well-defined concept of nothing. The nothing of modern physics is the quantum vacuum. And as we have seen, the quantum vacuum is far from being a true void. It is the lowest possible energy state of the universe's quantum fields. But this lowest energy is not zero. It is a seething, energetic sea of constant quantum fluctuations, a place where pairs of virtual particles are constantly bubbling into and out of existence. This is not a speculative idea. It is a direct consequence of the Heisenberg uncertainty principle, and its effects, like the Casimir effect, are experimentally measurable. The quantum vacuum, the nothing of physics, is a very rich and complex something. And it is from this rich and complex something that our universe is thought to have emerged. The theory of cosmic inflation posits that our universe was born from a tiny quantum fluctuation in a pre-existing high-energy false vacuum. In this scenario, the universe did not arise from an absolute philosophical nothingness. It arose from a pre-existing physical system, a quantum field, albeit one that was in a very different and unstable state. This just pushes the ultimate question back a step. Why did this false vacuum exist in the first place? Why did it have the specific properties that allowed for the birth of our universe? And what about the physical laws themselves? If absolute nothingness means the absence of everything, then it must also mean the absence of the laws of physics. So, how could a universe, with its intricate and consistent set of laws, emerge from a state where no laws existed? Did the laws somehow exist before the universe, in some abstract Platonic realm, waiting to be instantiated? If so, then these laws are themselves a form of something, and we are not starting from a true nothing. Or did the laws emerge with the universe? In which case, what was the principle that governed their emergence? This deep and tangled relationship between existence and the laws that govern it has led some philosophers and physicists to suggest that the very premise of the question is flawed. Perhaps something is the more natural, the more fundamental, the default state, and nothing is the difficult, and perhaps impossible, abstraction. The philosopher Robert Nozick, for example, speculated that nothingness might be inherently unstable, that there might be a kind of fecundity principle at play, a force that causes nothing to nothing itself, leading inevitably to the existence of something. Another related idea is that the total energy of the universe may be exactly zero. The positive energy of matter and radiation could be perfectly balanced by the negative gravitational potential energy. If this is the case, then the creation of the universe from the quantum vacuum would not violate the law of conservation of energy. It would be a free lunch, the creation of a zero-energy system from a zero-energy state. This is a beautiful and compelling idea, but it still relies on the pre-existence of the quantum vacuum and its laws. The puzzle remains. The persistent difficulty we have in even defining, let alone conceiving of, an absolute nothingness is a powerful clue. It suggests that our intuitive sense that nothing is the simpler and more natural state may be a profound and deeply ingrained cognitive error. We are beings of something, living in a universe of something, and our minds are tools that have evolved to navigate this reality. The concept of nothing, in its absolute form, may simply be a logical and psychological limit, a concept that points to the boundary of our own understanding, a boundary that we may never be able to cross. The story of our universe, as we currently understand it, begins with an event of almost unimaginable violence and creativity, the Big Bang. This is not a theory about an explosion in a pre-existing empty space. It is a theory about the beginning of space and time themselves, a theory about the evolution of our entire observable cosmos from a state of incredible and almost incomprehensible heat and density. Our scientific narrative can trace this story back to an astonishingly early moment, to a time just a tiny, infinitesimal fraction of a second after the beginning. At the Planck epoch, a time of roughly 10 to the power of minus 43 seconds, the entire observable universe was compressed into a space smaller than a single atomic nucleus. The temperature was a staggering 10 to the power of 32 Kelvin. In this primordial crucible, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces are thought to have been unified into a single, symmetric superforce. Our current laws of physics, the separate theories of general relativity and quantum mechanics, break down at this extreme scale. We do not yet have a complete theory of quantum gravity that can describe this earliest of all epochs. What happened at the precise moment of time zero, or what, if anything, came before it, remains the deepest and most profound mystery in all of science. But from the Planck epoch onwards, the story begins to come into sharper focus. The universe then entered a period of astonishing, hyper-accelerated expansion, a period known as cosmic inflation. Between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds, the universe expanded exponentially, growing by a factor of at least a trillion in the blink of an eye. This incredible stretching of the fabric of space-time smoothed out any initial irregularities and flattened its geometry, elegantly explaining the observed uniformity and flatness of our universe today. And most profoundly, inflation took the tiny, unavoidable quantum fluctuations of the primordial vacuum and stretched them to astronomical scales, planting the seeds for all the large-scale structure, the galaxies and the clusters of galaxies that we see today. At the end of inflation, the immense energy of the inflaton field that had been driving the expansion was converted into a hot, dense, and uniform soup of fundamental particles and radiation, an event known as reheating. This is the true, fiery beginning of the hot Big Bang phase of the universe's evolution, as the universe continued its rapid, but now more sedate, expansion. It began to cool. In the first few microseconds, the universe was a quark-gluon plasma, a state of matter so hot that even protons and neutrons could not exist. But as the temperature dropped, the quarks began to freeze out, binding together under the influence of the strong nuclear force, to form the first protons and neutrons. It was at this crucial early stage that a tiny, and still unexplained, asymmetry between matter and antimatter occurred. For every billion antiquarks, roughly one extra quark was created. This tiny 1 in a billion imbalance is the reason that our universe is made of matter and not just a sea of light. Over the next few minutes, in a process known as Big Bang nucleosynthesis, the protons and neutrons began to fuse together, forging the nuclei of the lightest elements. The universe at this time was like a vast cosmic nuclear reactor. The precise outcome of this primordial fusion was a universe made of roughly 75% hydrogen and 25% helium, with trace amounts of lithium. The remarkable agreement between these theoretical predictions and the observed abundances of these elements in the oldest stars is one of the most powerful and beautiful pieces of evidence for the Big Bang theory. For the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was so high that electrons could not bind to the newly formed atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, making the universe impenetrable to our view. But as the universe continued to expand and cool, it eventually reached a temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the nuclei, forming the first stable, neutral atoms of hydrogen and helium. This event is known as recombination. Suddenly, the cosmic fog lifted, the universe became transparent to light. The photons that had been trapped in the plasma were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelength stretched and cooled by the subsequent 14 billion year-long expansion of the universe, from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. Following the release of the CMB, the universe entered a period known as the Dark Ages, which lasted for several 100 million years. There were not yet any stars or galaxies to light up the cosmos. The universe was a vast, dark, and slowly evolving expanse of neutral hydrogen and helium gas. But it was not perfectly uniform. The tiny density fluctuations that had been imprinted during inflation were still there. And gravity, the patient and relentless architect of the cosmos, was beginning to go to work. The slightly denser regions began to attract more and more gas from their surroundings, their gravitational pull growing ever stronger. Over hundreds of millions of years, these collapsing clouds of gas became hot enough and dense enough at their centers to ignite the first nuclear fires. The first stars were born. The cosmic dark ages were over. The light was turned on. These first stars were likely very different from the stars we see today. They were forged from the pure primordial gas of the Big Bang, and were therefore made of only hydrogen and helium. They were likely incredibly massive, hundreds of times the mass of our sun, and they lived short, violent, and spectacular lives. In their fiery cores, they began the process of stellar nucleosynthesis, fusing the light elements into the heavier elements that are essential for the formation of planets and life: carbon, oxygen, nitrogen, iron. When these first massive stars died in spectacular supernova explosions, they scattered these newly forged elements into the interstellar medium, enriching the gas clouds from which the next generation of stars would be born. And so, the cosmic cycle of creation began. Gravity continued to pull these first stars and the enriched gas that surrounded them together, forming the first small dwarf galaxies. And these dwarf galaxies, in turn, merged and collided over billions of years, building up the grand spiral and elliptical galaxies like our own Milky Way that we see today. The story of the Big Bang is a story of profound and beautiful transformation. It is the story of how, from a state of almost perfect simplicity and uniformity, all the rich and complex structures of our universe were gradually born. It is a story of cooling, of expansion, of the patient and relentless work of gravity. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is a story that has been pieced together through a century of brilliant theoretical insights and painstaking observational discoveries. It is a story that tells us how our universe came to be, but it is a story that still leaves us with the deepest and most profound of all mysteries, the mystery of the why. The existence of our universe, a universe that is teeming with the intricate and beautiful structures of stars, galaxies, and life, is a profound and deeply puzzling fact. When we examine the fundamental physical laws and constants that govern our cosmos, we find that they appear to be exquisitely and almost miraculously fine-tuned for the emergence of complexity and consciousness. This is not a matter of philosophical speculation. It is a hard, quantitative conclusion drawn from our best and most precise scientific theories. The values of the fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton seem to fall within an incredibly narrow and seemingly arbitrary range of life-permitting values. If any of these numbers were even slightly different, the universe would have been a sterile, barren, and lifeless place. It is as if we have stumbled upon a cosmic recipe that has been calibrated with an almost impossible degree of precision. The initial expansion rate of the universe, for example, is a testament to this delicate balance. If the universe had expanded just a tiny fraction faster in its first second, matter would have been flung apart so quickly that gravity would never have had a chance to pull it together to form the stars and galaxies we see today. The universe would have remained a thin, diffuse, and featureless gas. If it had expanded just a tiny fraction slower, gravity would have quickly overwhelmed the expansion, causing the universe to recollapse into a big crunch long before any complex structures, let alone life, could have had time to form. The observed rate of expansion is balanced on a razor's edge, a perfect and seemingly improbable compromise that allows for a universe that is both long-lived enough and structured enough to support the slow, patient evolution of complexity. The fundamental forces of nature, the four pillars upon which our physical reality is built, also exhibit a remarkable and life-giving fine-tuning. The strong nuclear force, the powerful glue that binds protons and neutrons together in atomic nuclei, is a prime example. If it were just a few percent weaker, the electromagnetic repulsion between protons would tear apart any nucleus with more than one proton. The only element in the universe would be hydrogen. There would be no carbon, no oxygen, no iron, no chemistry, and no life. If it were a few percent stronger, the consequences would be equally catastrophic. Protons would bind together so readily that all the hydrogen in the early universe would have been quickly consumed in nuclear reactions, leaving no fuel for the long-lived, stable stars, like our Sun, that provide the gentle, consistent energy needed for life to evolve. The precise strength of the strong force is a cosmic sweet spot, a perfect balance that allows for a rich and diverse periodic table of the elements. The balance between the forces is also crucial. The electromagnetic force is about 10 to the power of 40 times stronger than the force of gravity. This immense discrepancy is essential. If gravity were much stronger, stars would be smaller, hotter, and would burn out in a geological instant. If it were much weaker, stars and galaxies would never have formed at all. The observed balance allows for gravity to dominate on the large cosmic scales, sculpting the galaxies and the cosmic web, while electromagnetism dominates on the small atomic scales, orchestrating the intricate dance of chemistry and life. The masses of the fundamental particles are another area of exquisite fine-tuning. A free neutron is slightly more massive than a proton, which allows it to decay into a proton, an electron, and an antineutrino. If the proton were slightly more massive than the neutron, it would be the proton that was unstable, and all the protons in the early universe would have decayed into neutrons. There would be no hydrogen, no stars, no water, no us. The tiny and seemingly arbitrary mass difference between these two fundamental particles is a prerequisite for our very existence. Perhaps the most celebrated and most astonishing example of fine-tuning is found in the heart of stars, in the process of stellar nucleosynthesis. All of the carbon in the universe, the very backbone of life, is forged in the cores of stars through a process called the triple alpha process, where 3 helium nuclei fuse together. This process is incredibly difficult, and it is only possible because of a miraculous coincidence in the energy levels of atomic nuclei. The British astronomer Sir Fred Hoyle in the 1950s realized that the observed abundance of carbon in the universe could not be explained by the known nuclear physics of his time. He predicted that there must be a previously unknown resonant energy level in the carbon-12 nucleus, an excited state that had just the right energy to dramatically increase the rate of the triple alpha process. He went to his experimentalist colleagues and implored them to look for this resonance, and to their astonishment, they found it, exactly where Hoyle had predicted it would be, without this specific and seemingly coincidental. Hoyle state, almost no carbon would be produced in the universe, but the story does not end there. The next step in stellar nucleosynthesis is the fusion of a carbon nucleus with another helium nucleus to form oxygen. If there were a similar resonance in the oxygen nucleus, then all the newly formed carbon would be quickly converted into oxygen, leaving none for the formation of life. As it turns out, the relevant energy level in the oxygen nucleus is just slightly off resonance, which allows for the production of both carbon and oxygen in roughly comparable amounts. the two most essential elements for life after hydrogen and helium. The universe seems to have been built on a series of these incredible, life-giving coincidences. The cosmological constant, the energy of empty space, is perhaps the most extreme example of all. Our best theories predict a value that is 120 orders of magnitude larger than what we observe. If it were this large, the universe would have been torn apart. The fact that it is so incredibly, exquisitely small is a profound and completely unexplained mystery. All of these examples, and many more, point to a universe that appears to be a setup, a put-up job, a place that is not just a random collection of physical laws and constants, but a finely tuned and beautifully coherent system that is, against all odds, perfectly suited for the emergence of complexity, and of beings like us who can marvel at its perfection. The universe we inhabit is a realm of profound and often bewildering contrasts. At the macroscopic level, the world of our everyday experience, things seem to be governed by the deterministic and intuitive laws of classical physics. A ball, when thrown, follows a predictable, parabolic path. The planets orbit the sun in a majestic, clockwork dance. Cause and effect are linked in a clear and unambiguous chain. But as we zoom in, as we probe the microscopic realm of atoms and subatomic particles, this classical common-sense picture dissolves into a reality that is fundamentally probabilistic, interconnected, and deeply strange. This is the world of quantum mechanics, a theory that has been stunningly successful in its predictions, but which continues to challenge our deepest intuitions about the nature of reality. One of the central and most bizarre features of this quantum world is the principle of superposition. In the classical world, an object can only be in one state at a time. A coin is either heads or tails. A cat is either alive or dead. But in the quantum world, a particle, as long as it is not being measured or observed, can exist in a superposition of multiple, mutually exclusive states simultaneously. An electron can be in a superposition of being in many different places at once. An atom can be in a superposition of having both decayed and not decayed. It is not that we simply do not know the particle's true state. The particle's true state is this ghostly to probabilistic blend of all possible states. This is a concept that is famously and absurdly illustrated by the thought experiment of Schrödinger's cat, a creature that is, until the moment of observation, both alive and dead at the same time. This strange superpositional nature of reality has been confirmed by countless experiments, most famously the double-slit experiment, where a single particle seems to pass through two slits at once, behaving like a wave and interfering with itself. Another cornerstone of quantum weirdness is wave-particle duality. Our classical intuition tells us that something is either a discrete, localized particle, like a grain of sand, or a continuous, spread-out wave, like a ripple on a pond. But quantum mechanics tells us that the fundamental constituents of our universe are both light, electrons, and even entire atoms can exhibit both wave-like properties, like interference and diffraction, and particle-like properties, like having a definite position when measured. Their nature is not a fixed, intrinsic property, but is dependent on the context of the experiment, on the question we ask of them. The act of observation seems to be what forces the quantum object to choose which of its dual natures to reveal. This leads to the observer effect, the strange and profound idea that the act of measuring a quantum system is not a passive act of discovering a pre-existing reality, but is an active process that helps to create that reality. The wave function, the mathematical object that describes the superpositional state of a quantum system, is said to collapse upon measurement, with one of the many possibilities being actualized. The nature of this collapse and the role of the observer remains one of the deepest and most unresolved mysteries in all of science. Furthermore, the quantum world is a world of quantization. Many physical properties, like the energy of an electron in an atom, are not continuous, but can only take on certain, discrete, specific values. An electron cannot have just any old energy. It must occupy one of a set of allowed energy levels. When it jumps from a higher level to a lower one, it emits a discrete packet, or quantum, of light, a photon, with a specific energy and color. This is the reason for the sharp, distinct spectral lines we see when we analyze the light from stars. And it is the fundamental reason that atoms are stable. The Heisenberg uncertainty principle adds another layer of profound strangeness. It is a fundamental, built-in limit to our knowledge. It states that there are certain pairs of properties, like a particle's position and its momentum, that cannot both be known with perfect precision at the same time. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of our technology. It is an intrinsic feature of the wave-like nature of reality. It means that the universe, at its core, is not a deterministic, clockwork machine, but a place of inherent, irreducible fuzziness and probability. And perhaps the most spooky of all quantum phenomena is entanglement. Two or more particles can become linked in such a way that their fates are intertwined. No matter how far apart they are separated, a measurement on one particle can instantly influence the state of the other, in a way that seems to defy the cosmic speed limit, the speed of light. This spooky action at a distance, as Einstein called it, has been experimentally confirmed time and time again. And it points to a deep, non-local, and holistic interconnectedness at the very heart of reality. The universe is not a collection of separate, independent things. It is a single, vast, and mysterious quantum system. These strange and beautiful quantum rules are not just an esoteric curiosity for physicists. They are the very foundation upon which our world is built. Without the stability of atoms, guaranteed by quantization, there would be no matter. Without the intricate dance of chemical bonds, governed by the electromagnetic force and quantum mechanics, there would be no complex molecules, no chemistry, no life. The weirdness of the quantum world is not a bug. It is a feature. It is an essential part of the perfect and often paradoxical recipe that allows for the existence of a complex, structured, and conscious universe. The observer effect in quantum mechanics, the strange and profound idea that the act of measurement helps to shape the reality being measured, is one of the most debated and philosophically challenging aspects of modern physics. It is a concept that seems to blur the line between the objective, external world, and the subjective, internal world of the observer. This is not just a matter of a clumsy measurement disturbing the system, like trying to measure the temperature of a cup of tea with a large, cold thermometer. It is a more fundamental and more mysterious process. At its core lies the collapse of the wave function. A quantum system, before it is measured, exists in a superposition of all its possible states, a ghostly cloud of potential described by the wave function. The act of measurement seems to force this cloud of possibilities to collapse into a single, definite, actualized state. But what precisely constitutes a measurement? Where does the strange, probabilistic world of quantum mechanics end, and the familiar, definite world of our classical experience begin? This is the measurement problem. And it is a deep, unresolved wound at the heart of the theory. The traditional Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, takes a pragmatic but philosophically cautious approach. It simply posits a fundamental divide, a shifty split, between the quantum world of microscopic systems and the classical world of our macroscopic measuring devices. When a quantum system interacts with a classical measuring device, the collapse just happens. The theory does not explain the mechanism of this collapse. It treats it as a fundamental and unexplained. feature of nature. This is a deeply unsatisfying answer for many, as it leaves the boundary between the quantum and classical worlds ill-defined, and elevates measurement to a special, almost mystical status. In response to this, other interpretations have been proposed. The many worlds interpretation, first conceived by Hugh Everett III in 1957, offers a radical and elegant solution: the wave function never collapses. The smooth, continuous evolution of the wave function, as described by the Schrödinger equation, is the only process that ever occurs when a measurement is made. The universe itself splits, or branches, into multiple parallel realities, one for each possible outcome. In one universe, the electron is detected at the top of the screen. In another, it is detected at the bottom. The observer also splits, with different versions of the observer experiencing different outcomes. In this view, reality is a constantly branching tree of possibilities, and we are just following one particular path through this vast multiverse. There is no special measurement process, no mysterious collapse, only the universal, deterministic evolution of the wave function of the whole cosmos. Another approach is the de Broglie-Bohm theory, or pilot wave theory. This interpretation posits that particles, like electrons, always have a definite, if unknown, position. They are real, objective entities, but they are guided in their motion by a pilot wave, a real physical wave that is described by the wave function. In the double-slit experiment, the pilot wave passes through both slits and creates an interference pattern, which then guides the particle to land in one of the bright bands on the screen. This restores a sense of objective, deterministic reality. But it does so at the cost of introducing a profound non-locality. The pilot wave is a holistic entity that can be influenced by events happening anywhere in the universe, instantaneously. A third class of theories, known as spontaneous collapse or objective collapse models, proposes that the collapse is a real physical process that happens randomly and spontaneously, independent of any observer. The collapse is a fundamental, new law of nature, a slight modification to the Schrödinger equation. For a single, isolated particle, the chance of a spontaneous collapse is incredibly small, so it can maintain its superposition for a long time. But for a macroscopic object, which consists of a vast number of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This is why we never see macroscopic objects like cats in a superposition. They are simply too large and complex to maintain their quantum coherence. Schrödinger's cat, the famous thought experiment that so beautifully illustrates the paradox of the measurement problem, is a powerful reminder of the deep conceptual chasm that separates the quantum and classical worlds. The cat in the box, suspended in its ghostly state between life and death, is a metaphor for the profound weirdness that ensues when we try to apply the rules of the micro-world to the world of our everyday experience, and the mystery is deepened still further by the quantum eraser experiment. This is a clever and subtle variation of the double-slit experiment, which shows that the past behavior of a quantum particle can be influenced by a choice made in the future. In this experiment, which path information is recorded, which destroys the interference pattern. But if this information is later erased in a way that makes it impossible to know which path the particle took, the interference pattern can be made to reappear, even if the erasure happens long after the particle has hit the detector screen. This suggests that the relationship between past, present, and future, between cause and effect, is far more subtle and interconnected in the quantum world than our classical intuition would ever allow. The observer effect, in all its strange and paradoxical glory, is not just a curiosity for physicists. It is a profound and fundamental challenge to our classical worldview. A challenge that suggests that reality may be a far more fluid, more interconnected, and more participatory process than we ever imagined. The unidirectional flow of time, the arrow of time, is one of the most fundamental and yet most mysterious aspects of our experience. We are born, we live, we die. We remember the past, but not the future. Cause always precedes effect. This seems so obvious, so deeply ingrained in the fabric of our reality, that we rarely stop to question it. But when we look at the most fundamental laws of physics, this arrow of time is nowhere to be found. The laws of Newtonian mechanics, of electromagnetism, of relativity, and even of quantum mechanics are all, with one minor exception related to the weak nuclear force, time-symmetric. They work just as well for a movie played forwards as for a movie played backwards. If you were to watch a video of individual atoms colliding, you often could not tell if the video was playing forwards or in reverse. The laws governing these tiny interactions do not inherently distinguish between past and future. So, if the microscopic laws are time-symmetric, why does time have such a clear and undeniable direction in our macroscopic world? The answer lies primarily in the second law of thermodynamics and the concept of entropy. Entropy is a measure of disorder, randomness, or the number of possible microscopic arrangements of particles in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time or remain constant, but it can never decrease. This law is not a fundamental law like gravity or electromagnetism. Rather, it is a statistical law. It is overwhelmingly probable that systems will evolve from states of lower entropy to states of higher entropy, simply because there are vastly more ways for a system to be disordered than ordered. Consider everyday examples. If you drop a glass, it shatters into many pieces. This is an increase in entropy, moving from an ordered state to a disordered state. It is theoretically possible for the pieces to spontaneously reassemble, but the probability of all the atoms and molecules in the glass randomly moving in precisely the right way at the same time to reconstruct the original glass is astronomically small, effectively zero. Similarly, a lump of sugar dissolves in coffee, spreading its molecules throughout the liquid. The reverse process, the sugar molecules spontaneously recollecting into a lump at the bottom of the cup, never happens. Heat always flows from a hot object to a cold object, never the other way around, because this process increases the overall entropy of the system. These irreversible processes define the thermodynamic arrow of time. The existence of this thermodynamic arrow of time in our universe is deeply connected to its initial state. For entropy to increase, the universe must have started in an incredibly low entropy, highly ordered state. The Big Bang, roughly 13.8 billion years ago, describes a universe that began as an extremely hot, dense, and remarkably uniform plasma. While incredibly hot, this state was also highly ordered in terms of its gravitational configuration. All the matter and energy were concentrated in a tiny volume, with very little gravitational clumping. This initial low entropy provided the room for entropy to increase over cosmic time, driving the evolution of the universe from a smooth, uniform state to one filled with complex structures like stars, galaxies, and life. If the universe had begun in a high-entropy, disordered state, it would have quickly reached a state of thermal equilibrium, where everything is uniformly distributed and nothing interesting happens. There would be no processes, no evolution, and no arrow of time. The origin of this initial low entropy is itself a profound cosmological puzzle, often referred to as the past hypothesis. Why did the Big Bang start with such incredible order? Beyond the thermodynamic arrow, there are other arrows of time that are ultimately linked to it. The cosmological arrow of time refers to the universe's continuous expansion. As the universe expands, its volume increases. matter and energy become more diffuse, and its overall entropy increases. This expansion provides a cosmic direction for time. If the universe were to eventually contract in a hypothetical Big Crunch, then the cosmological arrow would reverse, and entropy might decrease in that phase. But our current observations indicate an accelerating expansion. The radiative arrow of time refers to the fact that electromagnetic waves, such as light, always propagate outwards from their source, never converging inwards to a source. A light bulb emits light that spreads out. It does not absorb light from space to become brighter. This is also fundamentally connected to the second law of thermodynamics, as an inward converging wave would represent a highly ordered, low-entropy state that is statistically improbable to occur spontaneously. Finally, there is the psychological arrow of time, which is our subjective experience of time flowing from past to future. We remember the past, not the future. Our brains are structured to record information from past events, and our actions are aimed at influencing future outcomes. This psychological arrow is almost certainly a consequence of the thermodynamic arrow. The processes of memory formation, learning, and consciousness itself involve increasing the entropy of our brains and their environment. We build memories by creating ordered structures from disordered inputs, but the overall process of living and interacting with the world increases total entropy. The arrow of time is not just an abstract concept. It is what makes the universe dynamic and interesting. It allows for the formation of complex structures, from atoms to galaxies, and for the emergence of life and consciousness. It dictates that cause precedes effect, enabling predictable processes and the very possibility of scientific inquiry. Without the arrow of time, the universe would be a static, unchanging, or randomly fluctuating mess, devoid of the evolution, history, and complexity that define our existence. The fact that time flows in one direction, driven by the relentless march towards increasing disorder, is a fundamental property of our universe that enables everything we perceive and experience. The universe, in its fundamental design, appears to be a place of astonishing precision, almost as if it were calibrated with exquisite care for the emergence of complexity and life. This observation is often referred to as the concept of cosmic coincidences, or fine-tuning. It highlights that numerous fundamental physical constants and initial conditions of the universe possess values that fall within an incredibly narrow range, such that if they were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, chemistry, and ultimately, life as we know it. These are not merely fortunate accidents. They represent a series of highly specific parameters in a vast landscape of possibilities, making the existence of our universe seem remarkably improbable. One of the most striking examples of fine-tuning involves the strength of the strong nuclear force. This force, which binds protons and neutrons together to form atomic nuclei, is immensely powerful but acts only over incredibly short distances. If the strong force were just a few percent weaker, atomic nuclei beyond hydrogen would be unstable. Protons would repel each other too strongly due to the electromagnetic force, preventing the formation of elements like carbon, oxygen, and nitrogen, which are the building blocks of life. The universe would be a monotonous expanse of hydrogen and perhaps some helium. Conversely, if the strong force were just a few percent stronger, protons might bind too readily, perhaps forming stable diprotons or other exotic nuclei that would consume all hydrogen in the early universe. This would mean no water, no long-lived stars like our Sun, and a drastically different, likely lifeless, cosmos. The observed strength allows for a diverse range of stable elements and long-lived stars. The mass difference between a proton and a neutron is another crucial cosmic coincidence. A neutron is slightly more massive than a proton. This tiny mass difference, approximately 0.13% of the proton's mass, is vital. If the neutron were even slightly lighter than the proton, all protons in the early universe would have converted into neutrons. This would lead to a universe with no hydrogen, and thus no water, no long-lived stars, and a very different chemistry. If the neutron was significantly heavier, it would have decayed too quickly into a proton before Big Bang nucleosynthesis could produce sufficient helium. The precise mass difference ensures the right balance of protons and neutrons in the early universe, allowing for the formation of hydrogen and helium in the correct proportions, which are essential for stellar evolution and the subsequent creation of heavier elements. The strength of the electromagnetic force relative to the strong force in gravity is also finely tuned. Electromagnetism dictates how electrons orbit atomic nuclei and how atoms form molecules. If it were much stronger, electrons would be pulled too tightly to nuclei, preventing the formation of complex molecules. If it were much weaker, electrons might not form stable orbits, or atoms would be too diffuse. Furthermore, the ratio of the electromagnetic force to gravity is enormous, approximately 10 to the power of 40. This vast difference is essential. Gravity dominates on large scales, forming stars and galaxies, while electromagnetism dominates on atomic scales, allowing for chemistry. If gravity were much stronger relative to electromagnetism, stars would burn out too quickly, or the universe would be dominated by black holes. If electromagnetism were much weaker, matter might not clump into stars and galaxies effectively. Perhaps one of the most celebrated and most astonishing examples of fine-tuning involves the energy levels within carbon and oxygen atomic nuclei, particularly the Hoyle resonance. Carbon, with its 6 protons, is the backbone of all known life. It is primarily produced in the cores of stars when 3 helium nuclei fuse together. This triple alpha process is inherently difficult because the intermediate step, the fusion of 2 helium nuclei, forms an unstable beryllium-8 nucleus that quickly decays. For carbon-12 to form in sufficient quantities, there must be a specific energy level, or resonance, in the carbon-12 nucleus that precisely matches the energy of the fusing helium and beryllium nuclei. Sir Fred Hoyle, a British astronomer, predicted this resonance in the 1950s, arguing that its existence was necessary for carbon to be produced in the universe. Without this precise resonance, virtually no carbon would form, making carbon-based life impossible. Similarly, the energy level of oxygen-16 is also critical. It allows oxygen to form from carbon and helium, but it is just slightly off resonance enough to prevent all carbon from being converted into oxygen. This delicate balance ensures the cosmic abundance of both carbon and oxygen, the 2 most vital elements for life after hydrogen and helium. The cosmological constant, which represents the energy density of empty space, is another parameter exhibiting extreme fine-tuning. Its observed value is incredibly small, yet positive, by a factor of approximately 120 orders of magnitude smaller than theoretical predictions from quantum field theory. If the cosmological constant was significantly larger, its repulsive force would have caused the universe to expand so rapidly that matter could never have clumped together to form galaxies, stars, or any stable structures. The universe would have been a desolate, rapidly expanding void. If it were negative and too large, the universe would have collapsed back on itself almost immediately. The fact that its value is so tiny, allowing for both structure formation and accelerated expansion over billions of years, is a profound cosmic coincidence. Even the number of spatial dimensions we inhabit, 3, appears to be finely tuned for complexity. In a universe with only 2 spatial dimensions, complex structures like nervous systems or circulatory systems, which require intricate interconnections without crossing paths, would be difficult or impossible to form. Stable planetary orbits around stars are also problematic in 2 dimensions. In a universe with 4 or more spatial dimensions, the inverse square law of gravity would change, becoming an inverse cube law in 4 dimensions. For instance, this would cause planetary orbits to be unstable, spiraling inward or outward, and would likely prevent the formation of stable atoms, as electrons would not maintain stable orbits around nuclei. The existence of precisely 3 spatial dimensions seems essential for the kind of complex, stable structures that underpin life. Faced with the astonishing array of cosmic coincidences and the apparent fine-tuning of the universe's fundamental constants and initial conditions, scientists and philosophers have developed various interpretations. One of the most prominent is the anthropic principle. This principle, in its various forms, offers a way to understand why the universe appears to be so exquisitely suited for life, not by invoking a designer, but by considering the necessary conditions for the existence of observers like ourselves. It essentially turns the question around, rather than asking why the universe is fine-tuned. It asks what kind of universe we must inhabit, given that we exist to observe it. The most widely accepted and least controversial version is the weak anthropic principle. This principle states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist places where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In simpler terms, the WAP is a selection effect. If there were many universes or many regions within a single, vastly larger universe, each with different physical laws or different values for fundamental constants, then only those universes or regions that allow for the formation of stars, planets, and complex chemistry would be capable of hosting life. We, as observers, necessarily find ourselves in one of these life-permitting universes or regions. It is like finding yourself on a habitable planet with liquid water and a breathable atmosphere. You wouldn't find yourself on a barren, airless rock. So, observing a habitable planet is not surprising. It's a prerequisite for your presence. The WAP does not explain why the universe is fine-tuned, but rather explains why we observe it to be fine-tuned. It is a statement about our observational bias. The WAP gains significant explanatory power when combined with the multiverse hypothesis. If our universe is not the only one, but merely one among an enormous, perhaps infinite, ensemble of universes, then the apparent fine-tuning becomes less miraculous. In a multiverse, each universe could have different physical laws, different fundamental constants, and different initial conditions. In such a scenario, it is statistically inevitable that some universes would happen to have the precise combination of parameters necessary for the emergence of life. Our universe would simply be one of those rare, fortunate ones. We exist here because this is one of the few places where we could exist. The multiverse thus provides a framework for the WAP to function as a plausible scientific explanation for fine-tuning, shifting the question from why is this universe fine-tuned to how did the multiverse generate so many variations. Different theoretical models propose various types of multiverses. One prominent idea is the inflationary multiverse, arising from the theory of cosmic inflation. If inflation, the rapid expansion in the very early universe, is eternal, it could continuously spawn new bubble universes or pocket universes. Each of these bubbles could potentially have different physical laws and constants depending on how the scalar field driving inflation settles down. Another concept comes from string theory, which suggests that our universe exists on a brane within a higher dimensional space. String theory also predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants. If all these states are realized in different universes, then the fine-tuning of our universe could be explained by our selection bias within this landscape. A more controversial version is the strong anthropic principle. This principle states that the universe must have those properties which allow life to develop within it at some stage. This goes beyond mere observation and implies a deeper necessity or compulsion for the universe to be life-permitting. It suggests that the laws of physics are not just randomly chosen, but are somehow compelled to be life-permitting. Some interpretations of the SAP verge into teleological or even theological territory, implying that the universe was somehow designed or destined for life. However, most scientific discussions of the SAP interpret it as a stronger form of the WAP, suggesting that the very existence of fundamental laws or the initial conditions of the universe are such that they must lead to observers. The anthropic principle, particularly the multiverse interpretation, faces several criticisms. One major critique is its lack of empirical testability. If other universes exist, they are, by definition, beyond our observable horizon and cannot be directly accessed or measured. This makes the multiverse hypothesis difficult to falsify or verify through traditional scientific methods, leading some to argue that it falls outside the realm of science. Another criticism is that it shifts the problem of fine-tuning rather than solving it. If our universe is fine-tuned, then what about the multiverse itself? Is the multiverse fine-tuned to produce universes like ours? This can lead to an infinite regress of explanations. Furthermore, some argue that the anthropic principle is a tautology, a statement that is true by definition and therefore provides no new information. Of course, we must find ourselves in a universe that allows for our existence. This doesn't explain why such a universe exists in the first place. Despite these criticisms, the anthropic principle, especially the weak version combined with the multiverse, offers a compelling framework for addressing the fine-tuning problem without resorting to supernatural explanations. It transforms the apparent improbability of our universe into a statistical inevitability within a larger cosmic landscape, while it may not provide a definitive answer to the ultimate why question. It offers a powerful scientific perspective on why the universe appears to have a perfect recipe for life, by emphasizing the crucial role of observers in selecting the specific reality they inhabit. It forces us to confront the possibility that our universe might be just one of countless others, each a different roll of the cosmic dice. The universe, as observed by astronomers and physicists, appears to be remarkably fine-tuned for the existence of life. Numerous fundamental physical constants, such as the strength of gravity, the mass of the electron, and the initial expansion rate of the cosmos, possess values that fall within an incredibly narrow range. If these values were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, complex chemistry, and ultimately, life as we know it. This apparent cosmic coincidence has led to deep philosophical and scientific questions about why our universe seems to have such a perfect recipe. One of the most compelling and actively discussed theoretical frameworks attempting to address this fine-tuning problem is the multiverse theory. This concept proposes that our universe is not unique, but is merely one of an enormous, perhaps infinite, number of universes, each potentially possessing different physical laws, fundamental constants, and initial conditions. The core idea behind the multiverse is to transform the apparent improbability of our universe's fine-tuning into a statistical inevitability. If there are countless universes, each with a different set of physical parameters, then it becomes statistically probable, even guaranteed, that at least one of these universes would happen to have the precise combination of values necessary for the formation of stars, planets, and the emergence of life. In this scenario, our existence as observers means we necessarily find ourselves in one of these rare, life-permitting universes. This is the essence of the weak anthropic principle, which states that we observe the universe to be fine-tuned because only such a universe could support our existence. The multiverse provides the vast ensemble of possibilities required for the anthropic principle to be a plausible explanation, rather than a mere tautology. The concept of a multiverse arises from various theoretical extensions of our current understanding of physics, rather than being a single, unified theory. One prominent source of multiverse ideas stems from cosmic inflation, a widely accepted theory describing an extremely rapid, exponential expansion of the universe in its earliest moments. While standard inflation explains many features of our universe, such as its flatness and uniformity, some models of inflation, particularly those involving a scalar field that drives the expansion, suggest that inflation might not end everywhere simultaneously. Instead, quantum fluctuations in this field could cause inflation to stop in certain, localized regions, forming bubbles of space-time that become individual universes, while in other regions, inflation continues indefinitely, spawning new bubbles. This leads to the idea of eternal inflation, where an infinitely branching, self-reproducing, inflationary space-time continuously generates new universes. Each of these bubble universes, once formed, is essentially a separate Big Bang event. From the perspective of an observer inside one of these bubbles, their universe would appear to have originated from a singular point and expanded, just like our own. However, from the perspective of the larger, eternally inflating space-time, these bubbles are constantly being created and expanding within a larger, non-ending inflationary background. A key feature of these bubble universes is that they can possess different physical properties. The way the inflaton field decays and settles into a stable vacuum state can vary from one bubble to another. Each vacuum state corresponds to a different set of fundamental physical laws and constants. For example, in one bubble universe, the strength of gravity might be slightly different. In another, the mass of the electron might be larger, or the cosmological constant might have a different value. Some bubble universes might even have a different number of effective spatial dimensions or different types of fundamental particles. This vast diversity of properties across the ensemble of bubble universes is what makes the eternal inflation model a powerful candidate for explaining the fine-tuning of our own universe. If there are an infinite number of such bubbles, each with a random assortment of physical laws, then it is statistically inevitable that some of them will happen to have the precise combination of parameters necessary for the formation of stars, galaxies, chemistry, and ultimately, life. We, as observers, necessarily find ourselves in one of these rare, life-permitting bubbles. Another theoretical avenue for the multiverse comes from string theory and its extension, M-theory. String theory attempts to unify all fundamental forces and particles by proposing that the most basic constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles and forces. A key feature of string theory is that it requires the existence of more than the familiar 4 space-time dimensions. For the theory to be mathematically consistent, it often predicts 10 or 11 space-time dimensions. The reason we only perceive 4 dimensions is that the extra dimensions are thought to be compactified, or curled up into incredibly tiny, unobservable spaces. The way these extra dimensions are curled up, known as the Calabi-Yau manifold, can vary in an enormous number of ways, estimated to be as high as 10 to the power of 500 different possible geometries. Each of these geometries would correspond to a different set of physical laws and fundamental constants in the 4 large dimensions we experience. This vast number of possibilities is often referred to as the landscape of string theory. If each point in this landscape represents a different universe, then the universe we inhabit is simply one of the countless possibilities within this string landscape. The implications of a multiverse are profound. Firstly, it offers a purely naturalistic explanation for the universe's fine-tuning, reducing the need to invoke supernatural or teleological explanations. If there are infinite rolls of the cosmic dice, then it is no longer a miracle that one particular roll came up with the winning numbers for life. Secondly, it challenges the traditional view of our universe as the entirety of existence. Our observable universe, vast as it is, might just be a tiny speck within a much larger, incomprehensibly immense multiverse. Thirdly, it raises new questions about the origin and nature of the multiverse itself. If our universe requires an explanation for its existence, does the multiverse also require one? This can lead to an infinite regress of explanations, or suggest that the multiverse is a brute fact that simply exists without further cause. However, the multiverse theory also faces significant challenges and criticisms. The most prominent challenge is its lack of direct empirical testability. By definition, other universes in many multiverse models are causally disconnected from our own, meaning we cannot send signals to them, observe them directly, or interact with them. This makes it incredibly difficult, if not impossible, to gather direct observational evidence to confirm or refute their existence through traditional scientific methods. Some physicists argue that this lack of testability places the multiverse hypothesis outside the realm of empirical science, relegating it to philosophy or metaphysics. Proponents, however, argue that while direct observation might be impossible, indirect evidence could emerge, such as specific patterns in the cosmic microwave background radiation that might hint at collisions with other universes, or the discovery of new particles predicted by theories that also lead to a multiverse. Another challenge is the measure problem in infinite multiverses. If there are an infinite number of universes, how do we assign probabilities to different outcomes or properties? If every possible universe exists an infinite number of times, then any specific event, no matter how improbable, occurs infinitely often. This makes it difficult to make predictions or test the theory, as any outcome could be explained by some universe existing. Despite these challenges, the multiverse theory remains a powerful and elegant conceptual framework for addressing some of the deepest puzzles in cosmology, particularly the apparent fine-tuning of our universe, by embedding our reality within a much grander and more diverse cosmic tapestry. The concept of bubble universes emerges primarily from the theory of cosmic inflation, a cornerstone of modern cosmology that describes an extremely rapid, exponential expansion of the universe in its earliest moments. While the standard Big Bang model explains the universe's evolution from a hot, dense state, it faced several puzzles, such as the flatness problem, the horizon problem, and the monopole problem. Cosmic inflation, proposed in the 1980s, elegantly solves these problems by positing a brief but incredibly powerful burst of expansion. During inflation, which is thought to have occurred between approximately 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe expanded by an enormous factor, perhaps as much as 10 to the power of 26 or more. This rapid stretching smoothed out any initial irregularities, making the universe flat and uniform on large scales. The energy driving this expansion is typically attributed to a hypothetical scalar field, often called the inflaton field. This field possessed a high energy density that acted as a repulsive gravitational force, pushing space-time apart at an accelerating rate. At the end of inflation, the inflaton field decayed, converting its energy into the hot, dense soup of particles and radiation that constituted the initial conditions for the standard Big Bang expansion. The idea of bubble universes arises when we consider the possibility of eternal inflation. In many models of inflation, the inflaton field does not decay uniformly or simultaneously across all of space-time. Instead, quantum fluctuations within the inflaton field can cause inflation to stop in certain localized regions, while in other regions, the field continues to fluctuate and drive inflation. When inflation stops in a particular region, that region reheats and becomes a distinct bubble universe that begins to expand and evolve according to the standard Big Bang model. However, the surrounding space continues to inflate, creating new regions where inflation can end, thus spawning more bubble universes. This process can continue indefinitely, leading to an infinitely branching, self-reproducing, inflationary spacetime, a multiverse composed of an endless number of these causally disconnected bubble universes. Each of these bubble universes, once formed, is essentially a separate Big Bang event. From the perspective of an observer inside one of these bubbles, their universe would appear to have originated from a singular point and expanded, just like our own. However, from the perspective of the larger, eternally inflating spacetime, these bubbles are constantly being created and expanding within a larger, non-ending inflationary background. A key feature of these bubble universes is that they can possess different physical properties. The way the inflaton field decays and settles into a stable vacuum state can vary from one bubble to another. Each vacuum state corresponds to a different set of fundamental physical laws and constants. For example, in one bubble universe, the strength of gravity might be slightly different. In another, the mass of the electron might be larger, or the cosmological constant might have a different value. Some bubble universes might even have a different number of effective spatial dimensions or different types of fundamental particles. This vast diversity of properties across the ensemble of bubble universes is what makes the eternal inflation model a powerful candidate for explaining the fine-tuning of our own universe. If there are an infinite number of such bubbles, each with a random assortment of physical laws, then it is statistically inevitable that some of them will happen to have the precise combination of parameters necessary for the formation of stars, galaxies, chemistry, and ultimately, life. We, as observers, necessarily find ourselves in one of these rare, life-permitting bubbles. The scale of these bubble universes is immense. Each individual bubble can be unimaginably vast, perhaps even infinite in extent, and they are separated from each other by regions of still inflating space, which expands so rapidly that it prevents any interaction or communication between the bubbles. This means that even if another bubble universe were to collide with ours, we would likely never know it, as the event would occur in a region of space-time that is receding from us faster than the speed of light. While the concept of bubble universes arising from eternal inflation is a highly theoretical one, it emerges naturally from the mathematical framework of inflationary cosmology, which is widely accepted for its ability to solve the problems of the standard Big Bang model. It provides a compelling, naturalistic explanation for the apparent fine-tuning of our universe without resorting to a designer. However, it also presents significant challenges. The lack of direct observational evidence for other bubble universes remains a major hurdle, as their causal disconnection makes them inherently unobservable. Furthermore, the measure problem in infinite multiverses, which deals with how to assign probabilities to different outcomes in an infinite ensemble, remains an active area of research and debate. Despite these challenges, the idea of bubble universes offers a fascinating and powerful perspective on the origin and nature of our cosmos, suggesting that our universe might be just one tiny, habitable pocket within an infinitely larger, eternally expanding cosmic foam. The hypothesis that our universe and everything within it is in fact a highly sophisticated computer simulation is a fascinating and profoundly unsettling idea that challenges our fundamental understanding of reality. This concept, often explored in science fiction, has gained traction in philosophical and scientific circles, primarily driven by arguments about the potential capabilities of future advanced civilizations. It suggests that our perceived reality is not a fundamental, base reality, but rather an artificial construct, much like a virtual reality game, designed and run by a more technologically advanced civilization existing in a higher-level reality. The most compelling argument for the simulation hypothesis was put forth by the philosopher Nick Bostrom in 2003. His argument is based on a probabilistic trilemma. At least one of three propositions must be true. First, that civilizations almost never reach a post-human stage capable of running highly realistic simulations. This could be due to self-destruction, technological stagnation, or some other limiting factor. Second, that post-human civilizations, if they do arise, almost never run a significant number of ancestor simulations. This implies they might have no interest in simulating their past. Or they might consider it unethical, or they might simply prefer other forms of entertainment or research. Third, that we are almost certainly living in a simulation. If post-human civilizations are common, and if they are interested in running ancestor simulations, then the number of simulated realities would vastly outnumber the single, base reality. Therefore, statistically, it would be far more probable that we exist within one of these many simulations, rather than in the single, original reality. The argument relies on the assumption that the technological capacity to create highly realistic, conscious agent-filled simulations is achievable. Given the rapid advancements in computing power observed over the past decades, such a future seems plausible, at least conceptually. If our own civilization continues to advance at its current pace, it is conceivable that within centuries or millennia, we might possess the computational resources to simulate entire universes or historical periods with conscious beings. If we can, then it stands to reason that other, older, more advanced civilizations could already be doing so. While the simulation hypothesis is primarily a philosophical argument, some proponents point to certain features of our universe that, while not definitive proof, could be interpreted as evidence or glitches consistent with a simulated reality. One such feature is the fine-tuning of the universe's fundamental constants. As discussed in previous chapters, the precise values of gravity, electromagnetism, particle masses, and the cosmological constant seem perfectly calibrated for life. In a simulated universe, these parameters could simply be the settings chosen by the simulators to create a particular kind of environment or to achieve specific outcomes. This would explain the fine-tuning without resorting to chance or a divine creator. Another intriguing aspect is the quantum nature of reality. The probabilistic behavior of particles, the wave-particle duality, and the observer effect could be interpreted as computational optimizations. In a simulation, rendering every single particle in the universe at all times would be computationally expensive. Instead, the simulation might only render or compute the state of a particle when it is observed or interacted with. Much like a video game only renders the parts of the environment visible to the player. The inherent discreteness of reality at the Planck scale, the smallest possible units of length and time, could also be seen as the pixelation or computational resolution limit of the simulation. The mathematical nature of physical laws is also cited. The universe operates according to elegant and precise mathematical equations. This could simply be a reflection of its underlying computational code. Conservation laws, such as the conservation of energy and momentum, could be built-in rules of the simulation to ensure consistency. The finite speed of light could be a computational constraint, a maximum processing speed within the simulated environment. The Fermi paradox, which questions why we haven't detected any evidence of alien civilizations despite the high probability of their existence, could also be explained by the simulation hypothesis. Perhaps our simulation is limited to our observable universe, or other civilizations are simply not simulated within our particular instance. The philosophical implications of living in a simulated reality are profound. It raises questions about the nature of consciousness, free will, and purpose. If our reality is simulated, are our thoughts and emotions truly our own, or are they part of the program? What is the purpose of the simulation? Are we historical ancestors, experimental subjects, or simply entertainment? The identity of the simulators also becomes a question. Are they also simulated? This could lead to an infinite regress of simulations within simulations. However, even if we are simulated, our experiences, emotions, and relationships are real within the simulation. The suffering and joy we experience are not diminished by the fact that our reality might be running on a computer. Proving or disproving the simulation hypothesis is incredibly difficult. Direct evidence is unlikely, as the simulators would presumably make the simulation indistinguishable from base reality. Scientists might look for bugs or glitches in the fabric of reality, computational limits being hit, or subtle anomalies that suggest an artificial construct. However, any such anomaly could also be explained by new, undiscovered physics. Ultimately, the simulation hypothesis remains a powerful thought experiment that forces us to critically examine the nature of our existence and the limits of our perception, pushing the boundaries of what we consider real. The universe, in its profound complexity and underlying order, speaks a language that transcends human spoken words, the language of mathematics, from the smallest subatomic particles to the grandest cosmic structures. The fundamental workings of reality appear to be governed by precise mathematical laws and relationships. This pervasive mathematical nature of the cosmos is not merely a convenient tool for scientists to describe phenomena. It seems to be an intrinsic property of existence itself, leading to deep philosophical questions about why mathematics is so incredibly effective at describing the natural world. For centuries, thinkers have pondered this remarkable connection. Ancient Greek philosophers like Pythagoras believed that numbers held the key to understanding the universe, seeing mathematical ratios in musical harmony and celestial motions. Later, in the 17th century, Galileo Galilei famously asserted that the book of nature is written in the language of mathematics. This insight proved prescient, as the scientific revolution that followed was built upon the foundation of mathematical descriptions of physical reality. Consider Isaac Newton's laws of motion and universal gravitation, formulated in the late 17th century. These laws, expressed as elegant mathematical equations, precisely describe how objects move under the influence of forces and how masses attract each other. Newton's mathematical framework allowed for the accurate prediction of planetary orbits, the trajectory of projectiles, and the behavior of tides, ushering in an era of unprecedented scientific predictability. His work demonstrated that the seemingly chaotic movements of the heavens and the seemingly simple motions on Earth were governed by the same universal mathematical principles. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, again through a set of powerful mathematical equations. Maxwell's equations not only described all known electrical and magnetic phenomena, but also predicted the existence of electromagnetic waves which travel at the speed of light. This mathematical prediction was later confirmed by Heinrich Hertz's experiments in the late 1880s, demonstrating that light itself is an electromagnetic wave. This was a triumph of mathematical reasoning, revealing a deeper unity in nature that was not immediately apparent through observation alone. The 20th century brought even more profound mathematical revelations. Albert Einstein's theories of special and general relativity, developed in the early 1900s, fundamentally reshaped our understanding of space, time, gravity, and energy. These theories are expressed in highly sophisticated mathematical frameworks, particularly differential geometry for general relativity. Einstein's equations describe gravity not as a force, but as the curvature of space-time caused by mass and energy. These equations predicted phenomena such as the bending of light by massive objects, the existence of gravitational waves, and the precise orbital precession of Mercury, all of which have been confirmed with extraordinary accuracy. Similarly, quantum mechanics, the theory describing the behavior of matter and energy at the atomic and subatomic scales, is inherently mathematical. Concepts like wave functions, probability amplitudes, and the quantization of energy are all expressed using advanced mathematical tools, including linear algebra and complex numbers. Quantum mechanics predicts the discrete energy levels of atoms, the behavior of elementary particles, and the outcomes of particle interactions with astonishing precision. Many of its predictions, such as the existence of antimatter and the Higgs boson, were made purely through mathematical reasoning before experimental verification. This consistent success of mathematics in describing and predicting the physical world has led many to ponder its deeper significance. Eugene Wigner, a Nobel laureate in physics, famously wrote about the unreasonable effectiveness of mathematics in the natural sciences in 1960. He marveled at how abstract mathematical concepts, often developed for purely intellectual reasons without any immediate physical application in mind, later turn out to be precisely what is needed to describe fundamental aspects of the universe. For example, group theory, a branch of abstract algebra, found unexpected applications in describing the symmetries of elementary particles and the conservation laws that govern their interactions. Is mathematics invented by the human mind, a useful language we create to categorize and understand the world? Or is it discovered, an inherent structure of reality that exists independently of human consciousness? The remarkable predictive power and universal applicability of mathematics and physics suggests that it might be more than just a human construct. It implies that the universe itself is fundamentally structured in a mathematical way, that its laws are not arbitrary, but follow a deep, elegant, and consistent mathematical logic. The presence of symmetries in nature, which are beautifully described by mathematics, further reinforces this idea. Symmetries in physical laws often correspond to conservation laws. For example, the symmetry of physical laws under translation in time leads to the conservation of energy. Symmetry under translation in space leads to the conservation of momentum. The conservation of angular momentum is linked to the laws being the same regardless of orientation. These deep connections between abstract mathematical symmetries and conserved physical quantities reveal a profound mathematical elegance woven into the fabric of space-time. The universe's adherence to mathematical laws provides a framework for its predictability and order. Without this underlying mathematical structure, the cosmos would be chaotic and unpredictable, making scientific inquiry impossible. The fact that we can formulate theories, make predictions, and consistently verify them through observation and experiment is a testament to the universe's inherent mathematical coherence. This mathematical language is not just a description of what is. It is often a guide to what must be, revealing hidden truths about reality before they are directly observed. It suggests that the universe is not just a collection of random events, but a system built upon a foundation of logical and consistent mathematical principles, making its very existence and its capacity for complexity a profound mathematical marvel. Our everyday experience of the universe is confined to 3 spatial dimensions: length, width, and height, and 1 temporal dimension. Time, we move forward and backward, up and down, left and right, and always forward in time. This 4-dimensional space-time continuum, as described by Albert Einstein's theories of relativity, forms the familiar stage upon which all cosmic events unfold. However, many cutting-edge theories in modern physics propose the existence of additional dimensions beyond these familiar 4. These extra dimensions are not merely speculative concepts. They arise naturally from attempts to unify the fundamental forces of nature and to solve some of the deepest puzzles in physics, such as why gravity is so much weaker than the other forces. The idea of extra dimensions is not new. In the early 20th century, shortly after Einstein published his general theory of relativity, Theodore Kaluza and Oscar Klein independently proposed a theory that attempted to unify gravity and electromagnetism by introducing a 5th dimension. Their Kaluza-Klein theory suggested that if the universe had an extra spatial dimension, and if that dimension were curled up into a tiny, unobservable circle, then gravity propagating in this five-dimensional space-time would appear. From our four-dimensional perspective, to manifest as both gravity and electromagnetism. The strength of the electromagnetic force would be related to the size of this curled-up dimension. This was a groundbreaking idea, showing that seemingly disparate forces could emerge from a higher dimensional geometry. While Kaluza-Klein theory ultimately failed to fully unify all forces and predict the existence of all particles, it laid the conceptual groundwork for later theories involving extra dimensions. The key to understanding how extra dimensions could exist without being directly observable is the concept of compactification. Imagine a long, thin garden hose. From a distance, it looks like a one-dimensional line, but if you get very close, you can see that it has a second dimension, its circumference, curled up into a small circle. Similarly, physicists propose that extra dimensions might be curled up, or compactified, into incredibly tiny microscopic spaces, far too small for us to perceive directly with our current technology. These dimensions could be curled up into incredibly complex geometric shapes, often referred to as Calabi-Yau manifolds in string theory. The specific geometry of these curled-up dimensions would then dictate the fundamental physical laws and constants that we observe in our four large dimensions. The most prominent theory that necessitates extra dimensions is string theory and its more encompassing framework. M-theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles, such as electrons, quarks, and photons. For string theory to be mathematically consistent and free of anomalies, it requires the existence of 10 space-time dimensions. M-theory, which unifies various string theories, requires 11 space-time dimensions. The extra 6 or 7 spatial dimensions are thought to be compactified, curled up into complex Calabi-Yau shapes. The specific way these extra dimensions are compactified is crucial, as it determines the properties of the particles and forces we observe in our four-dimensional world. There are an enormous number of ways these dimensions can be curled up, estimated to be as high as 10 to the power of 500 different possible geometries. Each of these geometries would correspond to a different set of physical laws and constants. This vast array of possibilities is often referred to as the string landscape or the multiverse landscape. In this context, our universe, with its specific, fine-tuned laws, is simply one particular realization within this enormous landscape of possibilities, arising from a specific compactification of the extra dimensions. Another fascinating idea involving extra dimensions comes from brain cosmology, particularly models like the Randall-Sundrum models proposed in the late 1990s. In these models, our entire four-dimensional universe is envisioned as a brain, a higher-dimensional membrane embedded within a larger, higher-dimensional space called the bulk. In this scenario, ordinary matter and the fundamental forces are confined to our brain. However, gravity, unlike the other forces, is hypothesized to be able to propagate into the higher-dimensional bulk. This leakage of gravity into extra dimensions could explain why gravity appears so much weaker than the other fundamental forces from our four-dimensional perspective. The gravitational force we experience is only a fraction of its true strength, as much of its influence is diluted by spreading into the extra dimensions. This could potentially solve the hierarchy problem, which is the vast discrepancy between the gravitational scale and the electroweak scale. The search for experimental evidence of extra dimensions is a major frontier in physics. One approach involves looking for deviations from Newton's inverse square law of gravity at very small distances. If extra dimensions exist and gravity can propagate into them, then gravity's strength should increase more rapidly than the inverse square law at distances comparable to the size of these extra dimensions. Current experiments have tested gravity down to microscopic scales and have so far found no deviations, placing limits on the size of any large extra dimensions. Another avenue is to search for Kaluza-Klein particles at high-energy particle accelerators like the Large Hadron Collider. If extra dimensions are real, particles could have momentum in these curled-up dimensions, appearing to us as heavier versions of known particles. Detecting such particles would be a strong indicator of extra dimensions. Furthermore, some theories suggest that extra dimensions could affect the propagation of gravitational waves, offering another potential avenue for detection. If extra dimensions truly exist, they would radically alter our understanding of the universe. Our familiar four-dimensional spacetime would be merely a slice or a projection of a much grander, higher-dimensional reality. This would not only provide a framework for unifying all the fundamental forces, but also offer a compelling explanation for the fine-tuning of our universe's properties within the vast landscape of possibilities arising from different compactifications. The existence of dimensions beyond our perception would mean that the universe is even more intricate and mysterious than we currently imagine, constantly pushing the boundaries of our knowledge. The holographic principle is one of the most profound and counterintuitive ideas to emerge from theoretical physics in recent decades, suggesting that our three-dimensional reality might be, in some sense, a projection from a two-dimensional surface. The concept derives its name from a hologram, a two-dimensional photographic plate that encodes three-dimensional information, allowing a full, three-dimensional image to be reconstructed when illuminated correctly. In physics, the holographic principle posits that the description of a volume of space can be thought of as encoded on its boundary, much like a hologram. This means that all the information contained within a region of space, including everything inside it, could be entirely represented by data existing on its two-dimensional surface. This radical idea first emerged from the study of black holes in the 1970s and 80s. Stephen Hawking's work on black hole radiation and Jacob Bekenstein's insights into black hole entropy were pivotal. Bekenstein proposed that the entropy of a black hole, a measure of its internal disorder or the amount of information it contains, is not proportional to its volume, as one might intuitively expect for a three-dimensional object. Instead, he argued that a black hole's entropy is proportional to the area of its event horizon, the two-dimensional boundary beyond which nothing, not even light, can escape. This was a revolutionary idea because it implied that the maximum amount of information that can be contained within a region of space scales with its boundary area, not its volume. This concept was further developed by Gerard 't Hooft and Leonard Susskind in the 1990s, who generalized it into the holographic principle. They argued that if the maximum entropy of a region of space scales with its boundary area, it implies that the fundamental degrees of freedom, the basic bits of information that describe everything, are not located throughout the volume, but are instead stored on the boundary. It's as if the entire three-dimensional reality of the black hole's interior is somehow encoded on its two-dimensional surface. This is deeply counterintuitive because our everyday experience tells us that a larger volume can hold more information than a smaller surface. For example, a three-dimensional book contains more information than its two-dimensional cover. The holographic principle suggests that, at the most fundamental level, this intuition is wrong for space-time itself. The most concrete and powerful realization of the holographic principle comes from the ADSI-CFT correspondence, or anti-de Sitter/conformal field theory correspondence, sometimes called Maldacena duality. Proposed by Juan Maldacena in 1997, This is a profound mathematical conjecture that states that a theory of gravity in a particular type of curved spacetime, called anti-de Sitter space, is mathematically equivalent to a quantum field theory living on its boundary, which has one fewer dimension. For example, a theory of gravity in a 5-dimensional anti-de Sitter space is equivalent to a 4-dimensional quantum field theory living on its boundary. This correspondence is a duality because it provides two entirely different, yet mathematically equivalent, ways to describe the same physical reality. One description involves gravity and extra dimensions, while the other involves quantum particles and forces in a lower dimension. It's like having two different languages that perfectly describe the same set of phenomena. The ADS/CFT correspondence has been incredibly fruitful for theoretical physicists because it allows them to use the well-understood tools of quantum field theory to study difficult problems in quantum gravity, and vice versa. For instance, problems in strongly interacting quantum systems, like those found in high-temperature superconductors, can be mapped to simpler problems in gravity in a higher dimension. The implications of the holographic principle for our own universe are profound. Though it is important to note that the ADS/CFT correspondence applies to anti-de Sitter space, which has a negative cosmological constant, whereas our universe has a positive cosmological constant and is expanding. However, many physicists believe that the holographic principle is a more general feature of quantum gravity, and that some form of it might apply to our universe as well. If the holographic principle applies to our universe, it would mean that all the information describing our 4-dimensional spacetime and everything within it could, in principle, be encoded on a distant 3-dimensional boundary. This does not necessarily mean that we live in a computer simulation in the way discussed in the previous chapter, but it implies a deep and unexpected relationship between space, information, and gravity. It suggests that the fundamental reality might not be what we perceive as 3-dimensional space, but rather a more fundamental information-theoretic structure residing on a boundary. Our perceived reality would then be an emergent phenomenon, a holographic projection from this underlying information. This idea challenges our intuitive understanding of space as a fundamental container. Instead, space itself might be an emergent property arising from the entanglement of quantum degrees of freedom on a boundary. It suggests that the universe has a finite amount of information, and this information is stored on its surface, much like a cosmic hard drive. While direct experimental verification of the holographic principle in our universe remains a distant goal, it continues to be a powerful guiding principle. In the search for a unified theory of quantum gravity, offering a radical new perspective on the fundamental nature of reality and the very fabric of space-time, it hints that the universe's existence might be an intricate dance of information projected into the dimensions we perceive. At the very frontiers of our understanding of the universe lies a realm of existence so incredibly tiny and fleeting that our current theories of physics begin to break down. This is the Planck scale, a set of fundamental units of measurement length, time, mass, and temperature derived solely from universal physical constants, the speed of light, the gravitational constant, and the reduced Planck constant. These units, named after the pioneering German physicist Max Planck, who first introduced them in 1900, are not arbitrary. They represent the natural scales at which the effects of quantum mechanics and general relativity become equally important and inextricably intertwined. The Planck length is the smallest possible unit of length that has any physical meaning. It is approximately 1.6 times 10 to the power of minus 35 meters. To put this into perspective, if an atom were expanded to the size of the entire observable universe, a Planck length would still be smaller than a single atom. At distances smaller than the Planck length, The very fabric of spacetime is theorized to become so turbulent and foamy due to quantum fluctuations that our usual concepts of smooth space and time cease to apply. It is at this scale that the quantum nature of gravity, often referred to as quantum foam, is expected to manifest. Our current understanding of space-time, based on general relativity, describes it as a smooth, continuous manifold. However, at the Planck length, this smooth picture is expected to dissolve into a chaotic, probabilistic quantum realm. The Planck time is the smallest unit of time, approximately 5.4 times 10 to the power of minus 44 seconds. This is the shortest possible duration that has any physical significance. It represents the time it would take for light to travel one Planck length. In the context of the Big Bang, the Planck epoch, which lasted from the beginning of the universe up to one Planck time, is the earliest moment about which we can even theoretically speculate. Before this time, or within this incredibly brief interval, our current laws of physics are insufficient to describe what was happening. The universe was so hot and dense that quantum gravitational effects dominated, and space-time itself was likely in a state that defies our conventional understanding. The Planck mass is approximately 2.17 times 10 to the power of minus 8 kilograms, which is roughly the mass of a flea egg. While this might seem like a macroscopic mass compared to elementary particles, it is the mass at which a particle's Compton wavelength becomes equal to its Schwarzschild radius. In essence, a particle with the Planck mass, if compressed to the Planck length, would become a black hole. This unit is significant because it represents the scale at which the quantum effects of gravity become as strong as the gravitational force itself. Finally, the Planck temperature is an incredibly high temperature, approximately 1.4 times 10 to the power of 32 Kelvin. This is the maximum theoretical temperature representing the temperature of the universe at the Planck time. At such extreme temperatures, all known fundamental forces are believed to have been unified, and particles would have possessed energies far beyond anything we can recreate in laboratories. The significance of the Planck scale lies in the fact that it marks the boundary where our two most successful yet incompatible theories of physics, general relativity, describing gravity in the large-scale universe, and quantum mechanics, describing particles and forces at the microscopic level, both become relevant and equally important. However, these two theories, in their current forms, are not easily reconciled. General relativity describes gravity as the curvature of a smooth spacetime, while quantum mechanics describes particles and forces in terms of discrete quanta and probabilities. When one attempts to apply quantum mechanics to gravity, the calculations break down, leading to infinities that cannot be resolved. This fundamental incompatibility is the core reason why we lack a complete theory of quantum gravity. At the Planck scale, the very concepts of space and time as continuous entities may cease to be valid. Instead, space-time might be granular or foamy, composed of discrete units, much like a digital image is composed of pixels. This implies that there is a fundamental limit to how finely we can probe reality. We cannot meaningfully ask what happens at distances smaller than the Planck length or during intervals shorter than the Planck time, because the very notions of space and time lose their conventional meaning. The breakdown of physics at the Planck scale represents the ultimate edge of knowledge in our quest to understand the universe. It is the realm where the most fundamental questions about the origin of space-time, the nature of reality, and the unification of all forces must ultimately be answered. Theories like string theory and loop quantum gravity are attempts to construct a theory of quantum gravity that can describe physics at this extreme scale, providing a consistent framework that incorporates both general relativity and quantum mechanics. Understanding the Planck scale is not just an academic exercise, it is essential for a complete picture of the universe. including its earliest moments during the Big Bang and the ultimate nature of its existence. Despite the monumental achievements of science in unraveling the mysteries of the cosmos, humanity stands at a precipice, gazing into a vast expanse of the unknown. Our current scientific understanding, while profound, is far from complete. There are fundamental questions about the universe that remain unanswered, major phenomena that defy our current theoretical frameworks, and vast swaths of reality that lie beyond the reach of our present observational capabilities. This edge of knowledge is not a sign of failure, but rather a testament to the immense complexity of the universe and the ongoing nature of scientific inquiry. One of the most glaring gaps in our understanding is the nature of dark matter. We have compelling evidence for its existence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background, indicating that it makes up approximately 27% of the universe's mass-energy content. However, we do not know what dark matter is. It does not interact with light or other electromagnetic radiation, which is why it is invisible. It also does not seem to interact strongly with ordinary matter. Despite decades of dedicated experiments searching for weakly interacting massive particles, or WIMPs, the leading candidate for dark matter, no definitive detection has been made. The identity of dark matter particles remains one of the most significant unsolved problems in particle physics and cosmology, representing a huge missing piece in our cosmic inventory. Equally perplexing is dark energy, which accounts for roughly 68% of the universe's total mass energy. Its existence was inferred from the accelerating expansion of the universe. Discovered in 1998, dark energy acts as a repulsive force, pushing galaxies apart, and its energy density does not dilute as the universe expands. The simplest explanation is that it is the cosmological constant, the intrinsic energy of empty space. However, theoretical calculations of this vacuum energy from quantum field theory predict a value that is an astonishing 120 orders of magnitude larger than what is observed. This cosmological constant problem is the largest discrepancy between theory and observation in all of science, indicating a profound misunderstanding of either quantum mechanics, gravity, or both. Its nature and origin are completely unknown, yet it dictates the ultimate fate of the universe. The unification of quantum mechanics and general relativity represents arguably the greatest challenge at the edge of knowledge. Quantum mechanics successfully describes the microscopic world of particles and forces, while general relativity accurately describes gravity and the large-scale structure of the universe. Both theories are incredibly successful within their respective domains, but they are fundamentally incompatible. When one attempts to combine them, the calculations break down, leading to infinities. This means we lack a complete theory of quantum gravity, which is essential for understanding phenomena at extreme conditions, such as the very first moments of the Big Bang or the interior of black holes. Theories like string theory and loop quantum gravity are ambitious attempts to bridge this gap, but they are still under development and lack definitive experimental verification. Beyond these major components, there are numerous other fundamental questions. The origin of the universe itself remains deeply mysterious. While the Big Bang theory describes the evolution of the universe from an extremely hot, dense state, it does not explain what caused that initial state or what existed before it. Was there a singularity? Did the universe emerge from a quantum fluctuation in a pre-existing multiverse? The very first moments, before the Planck time, are beyond our current theoretical grasp. Similarly, the matter-antimatter asymmetry, why our universe is overwhelmingly made of matter when equal amounts of matter and antimatter should have been created in the Big Bang, is an unsolved puzzle. The mechanisms that led to this tiny, crucial imbalance are not fully understood. The nature of consciousness is another profound mystery that bridges physics, biology, and philosophy. How does subjective experience arise from physical matter? Is consciousness merely an emergent property of complex neural networks, or is there a deeper, more fundamental connection to the fabric of reality? While neuroscience continues to make strides in understanding brain function, the hard problem of consciousness explaining why physical processes give rise to qualitative experience remains elusive. Furthermore, the universe might contain phenomena or dimensions that are currently beyond our ability to detect or even conceive. The possibility of extra dimensions, as proposed by string theory, or the idea that our universe is a holographic projection from a lower dimensional boundary, challenges our fundamental understanding of space and time. These concepts, while mathematically elegant, push the boundaries of empirical verification. The edge of knowledge is not a static line. It is a constantly shifting frontier. Each scientific breakthrough, while providing answers, often reveals new, deeper questions. The discovery of dark matter and dark energy, for instance, solved some cosmological puzzles, but introduced even larger ones. This ongoing process of discovery and the recognition of what we do not know are essential drivers of scientific progress. The vastness of our ignorance underscores the incredible complexity and mystery of the universe, reminding us that its existence and our ability to ponder it are perhaps the greatest mysteries of all. For centuries, physicists have dreamed of discovering a single, overarching theoretical framework that could explain all the fundamental forces and particles in the universe. This ambitious quest is known as the search for a theory of everything, or TOE. The goal of a TOE is to unify general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, which describes the other three fundamental forces and the behavior of matter at the microscopic level. Such a theory would provide a complete and consistent description of all physical phenomena, from the Big Bang to the present day, and from the smallest subatomic particles to the largest galaxy clusters. The history of physics has been marked by successful unifications. In the 17th century, Isaac Newton unified celestial mechanics with terrestrial mechanics under his universal law of gravitation. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, demonstrating that light itself is an electromagnetic wave. In the 20th century, the Standard Model of particle physics successfully unified the electromagnetic force with the weak nuclear force into the electroweak force, and it also describes the strong nuclear force. The Standard Model, confirmed by numerous experiments including the discovery of the Higgs boson in 2012, is an incredibly successful theory, describing all known elementary particles and their interactions, except for gravity. However, gravity remains the outlier. Albert Einstein's general theory of relativity, which describes gravity as the curvature of space-time, is a classical theory. It works exceptionally well on large scales, explaining the orbits of planets, the bending of light by massive objects, and the expansion of the universe. But when attempts are made to incorporate gravity into the quantum mechanical framework, the mathematical calculations break down, leading to infinities and inconsistencies. This fundamental incompatibility between general relativity and quantum mechanics is the central obstacle in the search for a TOE. A theory of quantum gravity is needed to describe phenomena where both gravity and quantum effects are significant, such as in the extreme conditions of the very early universe or within the singularity of a black hole. Several theoretical approaches are being pursued in the quest for a TOE. The most prominent and extensively studied candidate is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles and forces. A key feature of string theory is that it naturally incorporates gravity. One of the vibration modes of a string corresponds to the graviton, the hypothetical quantum particle that mediates the gravitational force. For string theory to be mathematically consistent, it requires the existence of more than the familiar 4 space-time dimensions. Most versions of string theory require 10 space-time dimensions, while its overarching framework, M-theory, requires 11 dimensions. The extra dimensions are thought to be compactified, or curled up into incredibly tiny, unobservable spaces. String theory offers a compelling framework for unifying all 4 fundamental forces and all known particles within a single, consistent mathematical structure. However, it currently lacks direct experimental verification, as the energies required to probe the Planck scale are far beyond the capabilities of any foreseeable particle accelerator. Another leading candidate for quantum gravity is loop quantum gravity. Unlike string theory, which attempts to unify all forces, loop quantum gravity focuses specifically on quantizing gravity itself, without necessarily unifying it with the other forces initially. It proposes that space-time is not continuous, but is granular, or quantized, at the Planck scale. In this theory, space is made up of discrete loops or networks, and time also flows in discrete steps. This approach attempts to construct a quantum theory of gravity directly from the principles of general relativity and quantum mechanics. While loop quantum gravity offers a consistent picture of quantum space-time and has made progress in understanding black hole entropy and the Big Bang singularity, it also faces challenges, particularly in fully recovering classical general relativity at large scales and in making testable predictions. Other approaches to quantum gravity include causal set theory, which posits that space-time is fundamentally discrete and that events are ordered by a causal relationship. Non-commutative geometry, which suggests that space-time coordinates do not commute at the Planck scale. And twistor theory, which attempts to reformulate physics in terms of fundamental geometric objects called twistors. Each of these theories offers a unique perspective on how to reconcile gravity with quantum mechanics, but none has yet achieved the status of a fully verified TOE. The search for a TOE is driven by the belief that the universe should ultimately be governed by a single, elegant, and consistent set of laws. Such a theory would not only provide a deeper understanding of the fundamental nature of reality, but could also offer insights into some of the most perplexing mysteries in cosmology, such as the origin of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. It would allow physicists to describe the universe from the very first moments of the Big Bang, where all forces were unified, to its present state, and potentially predict phenomena beyond our current observational capabilities. However, the path to a TOE is fraught with challenges. The extreme energies and incredibly small scales at which quantum gravitational effects become dominant make direct experimental verification exceedingly difficult. The mathematical complexity of these theories is also immense. Despite these hurdles, the pursuit of a TOE remains the ultimate goal for many physicists, representing the pinnacle of human scientific endeavor. A quest to find the single, unifying principle that explains why the universe exists and how it all works. The search for one continues, pushing the boundaries of human intellect and revealing the profound depths of cosmic mystery. The universe operates with remarkable regularity and predictability, governed by a set of fundamental principles that physicists refer to as the laws of nature. These laws, expressed most precisely through the language of mathematics, dictate how matter and energy behave, how forces interact, and how the cosmos evolves. From the smallest subatomic particles to the grandest galaxy clusters, these laws appear to be universal, applying consistently across vast distances and immense timescales. They are unchanging, meaning the laws that governed the early universe are the same laws that govern it today, and they are deterministic in many contexts, allowing scientists to make precise predictions about future events. Yet, despite our increasing understanding of what these laws are and how they work, a deeper, more profound question remains: what is the origin and fundamental nature of these physical laws themselves? Are they arbitrary, a mere cosmic happenstance, or is there a deeper reason for their specific form and existence? One perspective views the laws of nature as inherent, fundamental properties of reality. In this view, they are not imposed from outside the universe, but are intrinsic to its very fabric, existing independently of any particular universe or observer. They are seen as necessary truths, perhaps even part of a larger, purely mathematical structure that simply is. This idea resonates with the unreasonable effectiveness of mathematics in describing the physical world, as noted by the physicist Eugene Wigner. If the universe is fundamentally mathematical, then its laws are simply expressions of that underlying mathematical reality. This perspective suggests that the laws could not have been otherwise. They are the only possible, consistent set of rules for a universe to exist. However, this raises the question of why these specific mathematical structures are realized, and why they are so perfectly conducive to complexity and life. A point that connects directly to the fine-tuning puzzle. Another viewpoint suggests that the laws of nature might be emergent properties, arising from a deeper, more fundamental level of reality. For instance, in some theories of quantum gravity, such as loop quantum gravity or certain approaches within string theory, space-time itself is not a fundamental, continuous background, but an emergent phenomenon built from more basic, discrete components. If space-time is emergent, then the laws of physics that operate within it might also be emergent, arising from the interactions of these more fundamental constituents. This would mean that the laws we observe are not truly fundamental, but are effective descriptions that apply at our particular scale of existence. This perspective offers a potential pathway to explain why the laws have their specific form. They are the macroscopic manifestation of simpler, underlying rules at the Planck scale. However, this merely pushes the question back a level. What are the laws governing these more fundamental constituents, and why do they exist? The concept of symmetries plays a crucial role in understanding the nature of physical laws. Many fundamental laws are deeply connected to symmetries in nature. For example, the conservation of energy is a consequence of the laws of physics being the same at all times. The conservation of momentum arises from the laws being the same at all locations in space. The conservation of angular momentum is linked to the laws being the same regardless of orientation. These symmetries are not just mathematical curiosities. They are profound statements about the universe's inherent order and consistency. But why does the universe possess these particular symmetries? Are they arbitrary choices, or are they somehow necessary for a consistent reality? The existence of these symmetries, which are beautifully described by group theory in mathematics, further blurs the line between a universe described by mathematics and a universe that is mathematics. The fine-tuning of the universe's constants, as discussed previously, adds another layer of complexity to the question of the nature of laws. If the laws are fixed and necessary, then their specific values, which appear so precisely calibrated for life, seem like an astonishing coincidence. If the laws are arbitrary, then their life-permitting values are an even greater coincidence. The multiverse hypothesis offers a potential resolution by suggesting that our universe is just one of many, each with different laws or different values for constants. In this scenario, the laws of our universe are not arbitrary in the grand scheme, but are simply one set among a vast ensemble. We observe these specific laws because only they permit our existence. However, this then raises the question of the meta-laws that govern the multiverse itself. What determines the distribution of laws across different universes? Are these meta-laws themselves arbitrary or necessary? The limits of scientific inquiry also come into play when pondering the nature of laws. Science excels at describing what the laws are and how they operate through observation, experimentation, and mathematical modeling. It can tell us that gravity follows an inverse square law or that particles obey quantum mechanical rules. But science, by its very nature, is less equipped to answer the ultimate why questions. Why do these laws exist in the first place? Why are they the specific laws that they are? This question often pushes into the realm of metaphysics and philosophy, beyond the empirical reach of current scientific methods. Some physicists argue that the laws simply are, that they are brute facts of existence for which there is no deeper explanation. Others continue to search for a more fundamental principle from which all laws could logically derive, perhaps a theory of everything that reveals a deeper, unavoidable necessity for the observed laws. The very concept of a law implies a regularity, a pattern that repeats. Without such regularities, the universe would be chaotic and unpredictable, making scientific understanding impossible. The fact that the universe adheres to these consistent mathematical rules allows for the emergence of order, complexity, and ultimately, consciousness capable of discerning these very laws. Whether these laws are fundamental, emergent, or selected from a larger ensemble, their existence and specific form are central to the universe's ability to exist in its currently observed, life-permitting state. The ongoing quest to understand the nature of these laws is a testament to humanity's enduring curiosity about the deepest foundations of reality. The universe, while governed by precise and consistent physical laws, also exhibits an undeniable element of randomness or chance. This interplay between determinism, where future states are perfectly predictable from initial conditions, and indeterminism, where outcomes are inherently probabilistic, is a profound aspect of reality. Understanding how much of what we see is due to fixed laws versus unpredictable chance events is crucial for a complete picture of the cosmos and our place within it. In classical physics, particularly the mechanics developed by Isaac Newton in the 17th century, the universe was largely seen as a deterministic clockwork. If one knew the precise position and momentum of every particle in the universe at a given instant, and all the forces acting upon them, then the entire future evolution of the universe could, in principle, be perfectly predicted. This idea was famously encapsulated by Pierre-Simon Laplace in the early 19th century, who imagined a hypothetical demon with such immense knowledge and computational power that it could foresee every event, past and future. In this classical view, chance was merely a reflection of our ignorance, a practical limitation on our ability to know all the necessary initial conditions. However, the advent of quantum mechanics in the early 20th century fundamentally challenged this classical deterministic worldview. At the microscopic level of atoms and subatomic particles, quantum mechanics introduces an inherent, irreducible randomness into the fabric of reality. This is not due to our lack of knowledge, but rather a fundamental property of nature itself. One of the cornerstones of quantum indeterminism is the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that there are certain pairs of properties of a quantum particle, such as its position and momentum, that cannot be known simultaneously with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This means that even if you knew everything possible about a particle at one moment, you could not perfectly predict its future trajectory, because its initial position and momentum cannot be simultaneously known with infinite precision. Furthermore, quantum mechanics describes particles existing in a superposition of multiple possible states until they are measured or observed. When a measurement is made, the wave function describing the particle's possibilities collapses into a single definite outcome. The specific outcome that occurs is fundamentally probabilistic. For example, a radioactive atom undergoes decay at a fundamentally random moment. While we can predict the half-life of a large sample of radioactive atoms, we cannot predict when any single atom will decay. This is not because we lack information about the atom, but because the event itself is inherently random at the quantum level. This quantum randomness is a genuine, irreducible element of chance in the universe. While individual quantum events are fundamentally random, their effects often average out at macroscopic scales. The vast number of particles involved in everyday objects means that their collective behavior often appears deterministic. For example, while the decay of a single radioactive atom is random, the overall decay rate of a large sample of atoms is highly predictable. This is why classical physics works so well for macroscopic phenomena. However, there are instances where quantum randomness can have macroscopic consequences, particularly in highly sensitive systems. The role of chance is evident throughout cosmic evolution. The very seeds of large-scale structure in the universe, the tiny density fluctuations from which galaxies and galaxy clusters eventually grew, are believed to have originated from random quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. These random quantum events, amplified to macroscopic scales, determined where the first stars and galaxies would form, and thus the overall distribution of matter in the universe. On Earth, biological evolution is a prime example of the interplay between chance and law. Genetic mutations, which introduce new variations into a population, are largely random events at the molecular level, often caused by errors in DNA replication or exposure to radiation. These random mutations provide the raw material for natural selection to act upon. Environmental changes, such as asteroid impacts, volcanic eruptions, or climate shifts, can also be viewed as chance events that drastically alter the course of evolution, leading to mass extinctions or new adaptive opportunities. The laws of natural selection then provide the deterministic framework for which traits are favored and how populations evolve over time. Without the element of random mutation, evolution would grind to a halt. Even in seemingly deterministic systems, chaos theory reveals how tiny, unpredictable variations in initial conditions can lead to vastly different outcomes over time. The butterfly effect, where a butterfly flapping its wings in Brazil could theoretically cause a tornado in Texas, illustrates how complex systems like weather patterns are inherently unpredictable in the long term, even if their underlying laws are deterministic. This is a form of practical unpredictability, distinct from the fundamental quantum randomness, but it highlights how chance can play a significant role in the unfolding of events. Ultimately, the universe appears to be a grand tapestry woven from threads of both fixed laws and unpredictable chance. The fundamental laws of physics provide the framework, the rules of the game, defining the possibilities and constraints for what can happen. They dictate how particles interact, how forces operate, and how space-time behaves. But within this framework, quantum randomness provides the inherent unpredictability at the most fundamental level, while chance events on larger scales introduce contingencies that shape the specific unfolding of cosmic and biological history. The universe is not a perfectly predictable machine, but a dynamic system where the interplay of law and chance leads to the rich, complex, and often surprising reality that we observe. The universe, at its most fundamental level, is described by a relatively small set of elementary particles and fundamental forces. Yet, from these simple building blocks and their interactions, an astonishing array of complex patterns, structures, and phenomena arise. This process, where intricate properties and behaviors emerge from the collective interactions of simpler components, is known as emergence. It is a concept that bridges different levels of scientific inquiry, explaining how the universe, despite its underlying simplicity at the deepest scales, can produce the incredible complexity we observe, from stars and galaxies to life and consciousness. Emergence means that the whole is greater than the sum of its parts. The properties of the complex system cannot be simply deduced by examining its individual components in isolation. A classic example of emergence comes from thermodynamics. The concepts of temperature, pressure, and entropy are not properties of individual atoms or molecules. A single atom does not have a temperature. However, when a vast number of atoms or molecules interact, their collective motion and collisions give rise to these macroscopic properties. Temperature, for instance, emerges from the average kinetic energy of the particles in a system. Pressure emerges from the force exerted by these particles colliding with the walls of a container. Entropy, a measure of disorder, emerges from the statistical arrangement of countless particles. The laws of thermodynamics, which describe how heat flows and how systems tend towards equilibrium, are emergent laws that arise from the underlying statistical mechanics of microscopic particles following simple rules of motion. In chemistry, the properties of molecules are emergent from the interactions of individual atoms. A water molecule, composed of 2 hydrogen atoms and 1 oxygen atom, has properties like being a liquid at room temperature, its solvent capabilities, and its high specific heat capacity that are entirely different from the properties of isolated hydrogen or oxygen atoms. These emergent properties arise from the specific electromagnetic bonds formed between the atoms and the resulting molecular structure. Furthermore, the self-assembly of complex biological molecules, such as proteins folding into intricate, three-dimensional shapes, or lipid molecules spontaneously forming cell membranes, are powerful examples of emergent order from simpler chemical rules. Perhaps the most profound example of emergent order is the emergence of life from non-living chemistry. Individual atoms and molecules are not alive. However, when vast numbers of specific molecules, such as DNA, proteins, lipids, and carbohydrates, interact in highly organized ways within a specific environment, they give rise to the emergent properties of life metabolism, reproduction, self-organization, and evolution. A single cell, a marvel of emergent complexity, operates through intricate networks of chemical reactions and molecular machinery, none of which, in isolation, possesses the property of life. Life emerges from the collective, dynamic organization of these non-living components on a larger scale. Consciousness is believed by many to be an emergent property of the incredibly complex network of neurons and their interactions in the brain. Individual neurons are simple, biological cells that fire electrical signals. However, when billions of these neurons are interconnected in intricate ways, forming vast neural networks with trillions of synapses, the emergent phenomenon of subjective experience, thought, emotion, and self-awareness arises. We cannot find consciousness by looking at a single neuron. It emerges from the collective activity of the entire system. In cosmology, the large-scale structures of the universe are emergent. The universe began from an almost perfectly uniform, hot, dense plasma. Over billions of years, gravity acting on tiny, initial density fluctuations caused matter to clump together. This process led to the emergence of stars, which are highly ordered, self-gravitating spheres of plasma. Stars then clustered into galaxies, which are vast, rotating systems of billions of stars, gas, and dark matter. Galaxies, in turn, are organized into galaxy clusters and superclusters, forming a vast, filamentary cosmic web. These hierarchical structures are emergent properties of the interplay between gravity, dark matter, and the expansion of the universe, arising from simple initial conditions and fundamental laws. The concept of emergence highlights that complexity does not necessarily require complex fundamental laws. Often, simple, Underlying rules, when applied repeatedly to a vast number of interacting components, can lead to surprisingly intricate and unpredictable patterns. Think of a cellular automaton like Conway's Game of Life, where simple rules for how cells turn on or off based on their neighbors lead to incredibly complex. Evolving patterns, including self-replicating structures. These systems demonstrate how local interactions can give rise to global order. Emergence is not a violation of the second law of thermodynamics, which states that total entropy tends to increase, while local pockets of order, like a living organism or a star, represent a decrease in entropy. This local decrease is always compensated by a much larger increase in entropy in the surrounding environment. For example, a star creates order by fusing light elements into heavier ones, but it radiates vast amounts of high-entropy energy into space. A living organism maintains its internal order by consuming low-entropy food and releasing high-entropy waste products and heat. The universe as a whole continues its march towards increasing disorder. But within this overall trend, pockets of remarkable order and complexity can emerge and persist for long periods. The universe's capacity for emergent order is a key reason why it is not just a featureless expanse, but a dynamic, evolving cosmos filled with diverse phenomena. It explains how, from a relatively simple beginning, the universe has unfolded into the rich, structured, and conscious reality that we observe. The existence of emergent order is a testament to the power of fundamental laws to generate complexity, making the universe's very existence and its ability to produce such intricate patterns a profound and beautiful mystery. The universe has always fascinated humanity, a vast and silent tapestry woven with unanswered mysteries. Yet, beyond the familiar cosmos of stars and galaxies, there may be more. Hidden dimensions, parallel realities, and entire worlds could exist just beyond the veil of our perception. The laws of physics as we know them might only be a local chapter in a much grander, more complex cosmic story. A design that stretches far beyond the confines of a single universe. It is this tantalizing possibility, this deep and enduring quest to understand the ultimate nature of reality, that has led humanity to build one of the most powerful and ambitious machines ever created, the Large Hadron Collider. This is not just an instrument of science. It is a time machine, a reality probe, a technological marvel designed to recreate the fiery, primordial conditions of the Big Bang and to unlock the deepest secrets of existence itself. Today, we embark on a journey into the heart of this scientific cathedral, an exploration that will take us from the colossal 27-kilometer ring buried deep beneath the Swiss-French border to the strange and beautiful realm of quantum collisions, where new and exotic forms of reality are forged for a fleeting, infinitesimal moment. We will explore the mind-bending concept of extra dimensions, the mysterious gravitational whispers of dark matter, and the ultimate philosophical challenge of a potential multiverse. Following the trail of the brilliant physicists and theorists who have dedicated their lives to this quest, we will examine the incredible discoveries that have already been made and the profound and often unsettling questions that still haunt the frontiers of our knowledge. Could our reality be just one of a vast and perhaps infinite number of other realities? Are there other parallel versions of ourselves, living out the consequences of every choice we never made? And will the Large Hadron Collider, in its relentless and powerful probing of the subatomic world, finally provide us with the first tantalizing hints of an answer? The search for the ultimate truth has begun, and it is a search that is taking place not in the distant heavens, but in the deep, dark, and wonderfully mysterious heart of matter itself. The Large Hadron Collider, or LHC, stands as a monument to human curiosity and collaboration. Nestled at CERN, the European Organization for Nuclear Research, and straddling the border between Switzerland and France, this immense machine is a 27-kilometer-long underground circular tunnel, a racetrack for the very building blocks of our universe. Its purpose is both elegantly simple and profoundly ambitious: to accelerate subatomic particles, like protons, to speeds just shy of the speed of light, and then to smash them together with an energy that has not been seen in the cosmos since the first fiery moments after the Big Bang. In the subatomic debris of these cataclysmic collisions, scientists search for the ghostly signatures of new particles, new forces, and new symmetries of nature, seeking clues to the deepest mysteries of our existence. The LHC is the culmination of a long scientific lineage, the latest and most powerful in a series of particle accelerators that have, over the last century, peeled back the layers of reality, revealing an ever deeper and ever stranger subatomic world. But the LHC was designed with a specific set of profound and long-standing questions in mind, questions that had brought the field of particle physics to a critical juncture. Physicists were grappling with the origin of mass. Why do some fundamental particles possess it, while others do not? They were hunting for the identity of dark matter, the invisible substance that makes up the vast majority of the matter in the universe, and they were trying to understand the deep and seemingly miraculous asymmetry between matter and antimatter, the reason our universe is made of stuff at all. The standard model of particle physics, the remarkably successful theory that describes all the known fundamental particles and their interactions, provides a beautiful and coherent framework for our understanding of the subatomic world. But it is an incomplete story. It has glaring omissions. It does not include the force of gravity. It has no explanation for dark matter or dark energy. It cannot account for the matter-antimatter imbalance. The LHC was conceived as a standard model-breaking machine, a powerful tool designed to find the cracks in our current understanding, the subtle anomalies that would point the way to a new, deeper, and more comprehensive theory of reality. The dream of a collider powerful enough to recreate the conditions of the early universe had been cherished by physicists for decades, but the technological hurdles were immense. It required the development of some of the most powerful superconducting magnets ever built, capable of generating magnetic fields thousands of times stronger than the Earth's, to bend the high-energy proton beams around the 27-kilometer ring. It required an ultra-high vacuum, emptier than interplanetary space, to ensure the proton beams could travel unimpeded on their journey. And it required the construction of some of the largest and most complex scientific instruments ever conceived, the massive cathedral-sized detectors like ATLAS and CMS that are designed to capture and to analyze the fleeting subatomic shrapnel of the particle collisions. After years of meticulous planning and a truly global collaborative construction effort involving thousands of scientists and engineers from over 100 countries, the LHC was finally completed and switched on in 2008. At its core, the science of the LHC is a form of cosmic archaeology. By smashing protons together with incredible energy, physicists are, for a fleeting, infinitesimal moment, recreating the hot, dense, and energetic conditions of the primordial universe. In that fraction of a second, new and exotic particles, some of which have not existed in nature since the Big Bang, can be forged from the pure energy of the collision, as described by Einstein's famous equation, E = mc². Many of these particles are incredibly unstable, decaying into more familiar particles in a fraction of a second. The job of the giant detectors is to act as a kind of high-tech, three-dimensional digital camera, to track the paths, the energies, and the identities of the hundreds of particles that fly out from each collision, and to reconstruct the story of what happened in that moment of creation. It is a process of sifting through a mind-boggling amount of data, trillions of collisions every second, to search for the rare, telltale signature of a new particle, a new force, a new discovery. It is a search for a needle in a cosmic haystack, a search that is pushing the limits of our technology, our computational power, and our very understanding of the fundamental nature of reality. The immense energy of the particle collisions at the LHC is the key to its scientific power. In the world of particle physics, higher energy translates directly to the ability to probe smaller distances and to create heavier, more exotic particles. The journey of a proton at the LHC is a journey of almost unimaginable acceleration. It begins in a simple bottle of hydrogen gas. The hydrogen atoms are ionized, stripped of their single electron, leaving bare protons. These protons are then injected into a series of smaller pre-accelerator rings, where they are given a kick of energy by powerful oscillating electric fields in radio frequency cavities. With each kick, they move faster, and their path is guided and focused by a complex array of magnets. As they gain speed, they are passed from one accelerator to the next, like runners in a relay race, until they are finally injected into the main 27-kilometer ring. Here, they will circle for hours, making over 11,000 laps every single second, their energy boosted with each turn by the powerful superconducting radio frequency cavities. The protons travel in two counter-rotating beams, each beam containing trillions of protons, all traveling at an incredible 99.9999991% of the speed of light. At this extreme relativistic speed, each proton has the kinetic energy of a flying mosquito, a seemingly tiny amount of energy, but an immense amount when concentrated into a single subatomic particle. At 4 specific points around the ring, these two hair-thin beams of high-energy protons are focused down to an even smaller size and are made to cross through each other. This is where the scientific magic happens. In the vast majority of cases, the protons in the two beams will simply pass by each other without interacting. But occasionally, two protons will collide head-on, releasing their immense, concentrated energy in a tiny subatomic fireball, a miniature Big Bang. It is in this fireball, for a fleeting, infinitesimal moment, that the conditions of the early universe are recreated. The raw energy of the collision is converted into a shower of new particles, a fleeting glimpse of the exotic zoo of particles that populated the cosmos in its first moments. And surrounding these collision points are the giant general-purpose detectors, ATLAS and CMS. These are marvels of modern engineering, multi-story structures packed with layers of different kinds of sensors, each designed to detect a different type of particle. The inner layers, closest to the collision, are silicon pixel and strip detectors designed to track the paths of charged particles with incredible precision. Surrounding these are the calorimeters, which are designed to measure the energy of the particles by absorbing them. And on the outermost layers are the muon chambers, which are designed to detect muons, a heavier cousin of the electron, which are one of the few particles that can punch through all the inner layers of the detector. The amount of data generated by these detectors is staggering. Each collision can produce thousands of particles, and there are billions of collisions happening every second. It is a torrent of information that is far beyond the capacity of any human to analyze. And so, a complex, multi-layered trigger system is used to filter the data in real time, selecting only the most interesting and potentially significant events to be saved for later analysis. This is a process that relies on sophisticated and increasingly AI-driven algorithms to search for the specific telltale signatures of new physics. The reason the LHC requires such high energies is not just to create new particles, but also to test the predictions of our current theories in a new and unexplored regime. The standard model of particle physics has been remarkably successful, but it is an incomplete theory. By pushing to higher and higher energies, physicists are hoping to find the limits of the standard model, to find a place where its predictions break down, a place that will point the way to a new, more fundamental theory of reality. The LHC is not just a machine for discovering new particles. It is a machine for discovering new questions, for pushing the boundaries of our knowledge, and for revealing the deep and often hidden structure of the universe itself. One of the most profound and long-sought answers that the LHC was built to provide was the confirmation of the existence of the Higgs boson. This elusive particle, first theorized in the 1960s by a group of physicists including Peter Higgs, was the missing cornerstone of the standard model of particle physics. It was the key to understanding one of the most fundamental and yet most mysterious properties of our universe: the origin of mass. The standard model, in its original and most elegant form, predicted that all the fundamental particles should be massless. But this is clearly not the case. We know that electrons, quarks, and the W and Z bosons all have mass. The Higgs mechanism was the brilliant theoretical solution to this puzzle. It proposed the existence of a new invisible energy field that permeates all of space, now known as the Higgs field. In the very early hot universe, this field was off and all the particles were massless. But as the universe cooled, the Higgs field underwent a phase transition and turned on, acquiring a non-zero value everywhere in the vacuum. And it is the interaction of the other fundamental particles with this background Higgs field that gives them their mass. Imagine moving through a thick, viscous liquid like molasses. A particle that interacts strongly with the Higgs field is like a person trying to wade through this molasses. It experiences a drag, an inertia, which we perceive as mass. A particle that interacts weakly with the field experiences less drag and has a smaller mass. And a particle that does not interact with the field at all, like the photon, experiences no drag and remains massless. The Higgs boson is the quantum particle associated with this field. It is a localized, vibrating excitation of the Higgs field itself, a ripple in the cosmic molasses. The standard model made a precise prediction for the properties of the Higgs boson, but it did not predict its mass. Finding the Higgs and measuring its mass was one of the primary goals of the LHC. The task was not an easy one. The Higgs boson is incredibly unstable, decaying into other, more familiar particles in an almost instantaneous fraction of a second. It is also incredibly rare, produced in only about 1 in every 10 billion proton-proton collisions at the LHC. The challenge for the experimentalists was to sift through the immense, chaotic debris of the collisions and to find the tiny, statistical excess of events that would signal the fleeting existence of the Higgs. It was a search that required the analysis of a truly astronomical amount of data, a task that pushed the limits of modern computing and statistical analysis. And then, on the 4th of July, 2012, in a historic and emotional announcement at CERN, the ATLAS and CMS collaborations jointly announced that they had, independently, discovered a new particle with a mass of about 125 gigaelectron volts, a particle whose properties were consistent with those of the long-sought Higgs boson. It was a moment of profound triumph for science, a confirmation of a 50-year-old theoretical prediction, and the culmination of one of the greatest and most ambitious scientific endeavors in human history. The discovery of the Higgs boson was a monumental achievement. It confirmed the existence of the Higgs field and provided the missing piece of the Standard Model puzzle. It gave us a deep and experimentally verified understanding of the origin of mass, one of the most fundamental properties of our reality. But in science, every answer seems to give rise to new and often deeper questions. And the discovery of the Higgs boson was no exception. While the particle's existence confirmed the general picture of the Higgs mechanism, its specific, measured properties have raised a host of new puzzles and have pointed the way towards a new and largely unexplored frontier of physics. For example, why is the mass of the Higgs boson so light? Quantum mechanics predicts that the Higgs mass should receive huge quantum corrections from its interaction with the virtual particles of the vacuum, which should drive its mass up to the Planck scale, the fundamental scale of quantum gravity, which is about 16 orders of magnitude heavier than what we observe. This hierarchy problem suggests that there must be some new physics, some new symmetry of nature, like supersymmetry. That is protecting the Higgs mass from these huge quantum corrections, but so far, the LHC has found no evidence for this new physics. Another profound mystery is the nature of the Higgs field's potential energy. The shape of this potential is what determines the stability of our universe's vacuum and the measured mass of the Higgs boson. When combined with the mass of the heaviest known particle, the top quark, suggests that our universe may not be in a truly stable, lowest energy state. It may be in a metastable, or false vacuum state, a state that is stable for now, but could one day, through a process of quantum tunneling, decay into a new, true vacuum state, an event that would rewrite the laws of physics and annihilate our entire cosmos in an instant. The Higgs boson, the very particle that gives our universe its substance, may also be the harbinger of its ultimate doom. Since 2012, the research at the LHC has shifted from a search for the Higgs to a detailed, precision study of its properties. By measuring its interactions with all the other known particles, and by searching for its potential interactions with new, as yet undiscovered, particles, physicists are hoping to use the Higgs boson as a portal, a window into the new physics that we know must lie beyond the Standard Model. The Higgs is not the end of the story. It is the beginning of a new chapter, a chapter that may lead us to a deeper understanding of dark matter, of quantum gravity, and of the ultimate fate of our universe. Despite the monumental success of the Standard Model and the triumphant discovery of the Higgs boson, the universe continues to present us with a host of deep and profound mysteries that lie beyond the reach of our current theories. The LHC, while confirming the last piece of the Standard Model puzzle, has, so far, failed to find any direct evidence for the new physics that we know must be there. This has led to a period of deep reflection and also of great excitement. In the world of particle physics, we are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. One of the most glaring and most humbling of these unsolved mysteries is the nature of dark matter. Our observations of the cosmos, from the rotation speeds of galaxies to the gravitational lensing of distant light, have provided overwhelming and incontrovertible evidence that the visible matter of our universe, the stars, the gas, the dust, is just the tip of a vast cosmic iceberg. About 85% of the matter in the universe is made of a mysterious, invisible substance that does not interact with light. It is dark. We know it is there because we can feel its gravitational pull, but we have no idea what it is. The standard model of particle physics has no place for dark matter. None of the known particles have the right properties to be the dark matter. This means that the vast majority of the matter in the universe is made of something new, something completely outside of our current and otherwise incredibly successful theory of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a hypothetical particle, predicted by theories like supersymmetry, that would be heavy and would interact only through the weak nuclear force and gravity. This was an attractive idea, because a WIMP with the right mass and interaction strength would have been produced in just the right abundance in the early universe to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and multi-pronged experimental search. But after decades of searching in deep underground laboratories with satellite-based telescopes and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a WIMPless era in particle physics, a time of great creativity and of a renewed search for alternative dark matter candidates. Perhaps dark matter is made of actions, a hypothetical ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Or perhaps it is made of sterile neutrinos, a heavier and even more elusive cousin of the known neutrinos. Or perhaps it is part of a whole, hidden, dark sector of particles and forces that interacts with our own visible world only through very weak or portal interactions. Another profound and equally challenging mystery is the nature of antimatter. According to the laws of physics, the Big Bang should have produced matter and antimatter in almost perfectly equal amounts. But when a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the early universe had been perfectly symmetric, all the matter and antimatter would have been destroyed, leaving behind a cold, empty universe filled with nothing but photons. The very fact that we exist, that the universe is filled with galaxies, stars, and planets made of matter, is a testament to a deep and as yet unexplained asymmetry in the laws of nature. In the first moments of the universe, for some reason, a tiny excess of matter was created about one extra particle of matter for every billion particle-antiparticle pairs. All the substance of our universe is the leftover remnant of this primordial symmetry-breaking event. The standard model does contain a small amount of CP violation, a subtle difference in the way matter and antimatter behave. But it is far too small to account for the observed dominance of matter in the cosmos. There must be a new source of CP violation, a new physics beyond the standard model, that is responsible for our very existence. The LHC is searching for this new physics by studying the decays of certain rare particles, like B mesons, with incredible precision, looking for any tiny deviation from the predictions of the standard model that could signal a new asymmetric interaction. And then there is the ultimate challenge, the holy grail of modern physics, the unification of gravity with quantum mechanics. The standard model is a quantum theory, but it does not include gravity. Einstein's general theory of relativity is our best theory of gravity, but it is a classical theory. The search for a quantum theory of gravity that can consistently describe both the very large and the very small is the great unfinished revolution of 20th century physics. Some theories, like string theory, propose a radical solution, the existence of extra hidden dimensions of space. In these theories, the weakness of gravity compared to the other forces could be explained by the fact that gravity is the only force that can leak out into these extra dimensions. The LHC is searching for evidence of these extra dimensions by looking for the production of microscopic black holes or for the signature of Kaluza-Klein particles, the heavy copies of the known particles that would be the result of their vibration in the extra dimensions. The absence of answers to these profound questions is not a sign of failure. It is a sign that we are standing at the threshold of a new and deeper understanding of the universe. The LHC, with its ongoing upgrades and its ever-increasing precision, remains our most powerful tool for probing this new frontier. It is a machine that is designed not just to find answers, but to ask new and more profound questions. And in the subtle anomalies, the unexpected results, the things that don't fit our current theories, may lie the clues that will lead us to the next great revolution in our understanding of the deep, beautiful, and wonderfully mysterious nature of reality. The Standard Model of particle physics is one of the crowning achievements of modern science. It is a beautiful and remarkably successful theory that describes the fundamental subatomic constituents of our universe and the forces that govern their interactions. It is a testament to the power of human reason to uncover the deep mathematical order that underlies the seeming chaos of the physical world. At its core, the Standard Model is a kind of periodic table of the fundamental particles. It organizes the known particles into three fundamental categories. The first are the quarks, which are the building blocks of the protons and neutrons that make up the atomic nucleus. There are 6 flavors of quarks, which come in 3 generations of increasing mass: the up and down quarks, the charm and strange quarks, and the top and bottom quarks. The second category are the leptons, which are the other fundamental matter particles. The most famous of these is the electron, which orbits the atomic nucleus and is responsible for all of chemistry. The electron also has 2 heavier cousins, the muon and the tau, and each of these 3 charged leptons has a corresponding, nearly massless and incredibly elusive partner, the neutrino. The third category are the gauge bosons, which are the particles that mediate the fundamental forces of nature. The photon is the carrier of the electromagnetic force. The gluons are the carriers of the strong nuclear force, the force that binds the quarks together inside protons and neutrons. And the W and Z bosons are the carriers of the weak nuclear force, the force that is responsible for certain kinds of radioactive decay. And finally, there is the Higgs boson, the particle associated with the all-pervading Higgs field, which, as we have seen, is responsible for giving mass to many of the other fundamental particles. This elegant and relatively simple cast of 17 fundamental particles and the mathematical framework of quantum field theory that describes their interactions has been able to explain, with incredible precision, the results of virtually every particle physics experiment that has ever been performed. It is a theory that has been tested and confirmed to an astonishing degree of accuracy. And yet, for all its success, we know that the Standard Model is not the final word. It is an incomplete theory, a beautiful but partial chapter in the grand book of reality. It has a number of profound and glaring omissions. Most famously, it does not include the force of gravity. It has no explanation for the existence of dark matter and dark energy, the mysterious, invisible components that make up 95% of the energy content of the universe. It does not explain the observed asymmetry between matter and antimatter. And it has a number of free parameters, about 19 of them, like the masses of the particles and the strengths of the forces, whose values are not predicted by the theory, but must be measured experimentally. These are not just minor details. They are deep conceptual cracks in the foundation of our current understanding, cracks that point towards the existence of a new and more fundamental layer of physical reality. The search for this new physics beyond the standard model is the primary occupation of modern experimental and theoretical particle physics, and there are a number of compelling theoretical ideas that offer a glimpse of what this new physics might look like. One of the most elegant and most popular of these is the idea of supersymmetry, or SUSY. Supersymmetry is a hypothetical, new symmetry of nature that would relate the two fundamental classes of particles, the fermions, which are the matter particles like quarks and leptons, and the bosons, which are the force-carrying particles. In a supersymmetric world, every known fermion would have a corresponding superpartner boson, and every known boson would have a corresponding superpartner fermion. The electron would have a superpartner called the selectron. The quark would have a squark. The photon would have a photino. The Higgs boson would have a Higgsino. This doubling of the particle zoo may seem like a complication, but it is a complication that has the potential to solve a number of the deep problems of the standard model at once. For example, the existence of these new supersymmetric particles would naturally and elegantly solve the hierarchy problem, the puzzle of why the Higgs boson is so light. The quantum corrections to the Higgs mass from the standard model particles would be almost perfectly cancelled by the contributions from their superpartners, keeping the Higgs mass naturally small and stable. Supersymmetry also provides a natural candidate for the dark matter particle. In most supersymmetric models, the lightest supersymmetric particle is stable, and it would have just the right properties, being massive and interacting only weakly with normal matter to be the dark matter that we observe in the cosmos. And finally, at very high energies, the strengths of the three forces of the standard model, when extrapolated using the equations of supersymmetry, seem to converge to a single, unified value, a tantalizing hint of a grand unified theory where the three forces are just different aspects of a single underlying force. For all these reasons, the search for supersymmetry has been one of the primary goals of the Large Hadron Collider. But after more than a decade of searching, the LHC has, so far, found no evidence for these new supersymmetric particles. This has led many to question the validity of the simplest and most natural supersymmetric models, and to explore other, more complex, or more hidden, versions of the theory. Another, and equally profound idea for physics beyond the standard model is the existence of extra hidden dimensions of space. As we have seen, theories like string theory require the existence of 10 or 11 space-time dimensions to be mathematically consistent. The idea is that the extra spatial dimensions are compactified, curled up into a tiny, and for us, invisible shape. But these extra dimensions could have real and potentially detectable physical consequences. They could help to explain the weakness of gravity, and they could provide a home for new particles and new forces. The search for these extra dimensions at the LHC is a search for strange and unexpected experimental signatures, like the production of microscopic black holes, or the observation of a tower of heavy Kaluza-Klein particles, which would be the extra-dimensional copies of the known standard model particles. And then there is the possibility of entirely new and as yet unimagined fundamental forces and particles. The standard model has a very specific and somewhat arbitrary structure. There is no deep theoretical reason why there should be exactly 3 generations of quarks and leptons, or why the forces should have the specific mathematical structure that they do. It is possible that there is a whole new dark sector of particles and forces that is hidden from us, a sector that interacts with our own visible world only through very weak or portal interactions. Dark matter could be a part of this dark sector, and the LHC, with its high energies and its incredible sensitivity, is a powerful tool for searching for the subtle, indirect signatures of this hidden world. The absence of any clear, unambiguous signal of new physics at the LHC beyond the Higgs boson, has been a source of both frustration and excitement in the particle physics community. It is frustrating because the simple and elegant solutions to the problems of the Standard Model, like supersymmetry, have not yet materialized. But it is also exciting because it means that the universe is more subtle, more clever, and more mysterious than we thought. The path to a deeper understanding is not as straightforward as we might have hoped, and it will require a new generation of more powerful experiments, and perhaps a new generation of even more creative and more radical theoretical ideas. The story of the universe is far from over, and the Standard Model, for all its beauty and its success, is just the beginning of the story. The idea that our familiar or four-dimensional universe may be just a small slice of a much larger and much more complex. Multidimensional reality is one of the most mind-bending and transformative concepts in all of modern physics. It is an idea that has its roots in the early 20th century, but it has been given a new and powerful life by the development of modern unified theories like string theory. The quest to unify gravity with the other forces of nature has led physicists down a path that seems to inevitably point towards the existence of extra hidden dimensions of space. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the mathematical consistency of this theory requires that these strings must be vibrating in a space-time that has more than the 4 dimensions we are familiar with, typically 10 or 11 dimensions in total. So, where are these extra dimensions? Why do we not see them in our everyday lives? The standard answer is that they are compactified, curled up into a tiny, intricate, and for us, invisible, geometrical shape at every point in our 3-dimensional space. Imagine a tightrope walker from a great distance. The rope appears to be a one-dimensional line. The walker can only move forwards or backwards. But for a tiny ant on the rope, there is another and very real dimension, the circular dimension that goes around the rope. The ant can move forwards and backwards, but it can also move around the rope. The extra dimensions of string theory are like this circular dimension of the rope, but they are curled up on a scale that is unimaginably small, the Planck length, which is why we do not perceive them directly. But these extra dimensions are not just a mathematical curiosity. They have profound physical consequences. The precise shape and size of this compact, 6 or 7-dimensional Calabi-Yau manifold is what determines the properties of the strings, and therefore, the properties of all the particles and forces of our universe. The laws of physics are a reflection of the geometry of these hidden dimensions. This is a breathtakingly beautiful and ambitious idea. It suggests that the deep, and often seemingly arbitrary, structure of our universe is a consequence of a hidden, higher dimensional geometry. But the existence of extra dimensions has also led to another, and equally radical, idea: the brain world scenario. In this picture, our entire 4-dimensional universe is a brain, a subspace that is floating in a higher dimensional bulk. The particles and forces of the Standard Model are confined to our brain. They are like drawings on a sheet of paper that cannot leave the surface. But gravity, the geometry of space-time itself, is a property of the entire higher dimensional bulk, and it is free to propagate through the extra dimensions. This could provide a beautiful and elegant solution to the hierarchy problem. The puzzle of why gravity is so much weaker than the other forces. The gravitational force is not intrinsically weak. It just appears weak to us because its influence is being diluted, spread out over the extra hidden dimensions. Our brain is only feeling a small fraction of its true higher dimensional strength. The brain world scenario opens up a host of new and truly extraordinary cosmological possibilities. There could be other parallel brains, other universes, floating nearby in the bulk, separated from us by a tiny distance in a fifth dimension. This is a different kind of multiverse than the bubble universe picture of eternal inflation. It is a multiverse of stacked, parallel realities. And it is a multiverse that could, in principle, have observable consequences. While we cannot directly travel to these other branes, we could potentially interact with them through the one force that can travel through the bulk gravity. The mysterious, invisible dark matter that fills our universe could be the gravitational influence of ordinary matter that is confined to a nearby parallel brane. We cannot see the matter on that shadow brane because light and the other standard model forces are trapped on it, but we can feel its gravitational pull. The Big Bang itself could have been the result of a collision between our brane and another, a cataclysmic event in the higher dimensional bulk that released the energy to create our entire cosmos. This ekpyrotic, or cyclic model, as we have seen, provides a compelling alternative to the standard inflationary picture of our cosmic origin. The search for evidence of these extra dimensions is one of the most exciting and active frontiers of modern experimental physics. The Large Hadron Collider is at the forefront of this search. If the extra dimensions are large enough, then the high-energy collisions at the LHC could have enough energy to kick a particle off of our brane and into the bulk. This would manifest in the detectors as missing energy, a clear and unambiguous signal that something has escaped from our familiar four-dimensional world. The LHC could also, in some of these models, have enough energy to create tiny, microscopic black holes. These would not be the dangerous, galaxy-devouring black holes of astrophysics. They would be tiny, fleeting, quantum gravitational objects that would evaporate almost instantly in a shower of Hawking radiation. The detection of such an event would be a stunning and Nobel Prize-winning confirmation of the existence of extra dimensions and a direct window into the strange and beautiful world of quantum gravity. So far, the LHC has found no evidence for either missing energy or microscopic black holes. This has placed tight constraints on many of the simplest and most natural extra-dimensional models, but the search continues. The universe may be more subtle, more clever, and more multidimensional than we have yet been able to probe. The idea of hidden dimensions is a concept that pushes the limits of our scientific imagination. But it is an idea that is born from the deep, mathematical logic of our best and most ambitious physical theories. And it is an idea that reminds us that the reality we perceive with our senses may just be a shadow, a fleeting and partial projection of a much richer, much deeper, and much more wonderfully complex multidimensional cosmos. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes, is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that has migrated from the pages of science fiction to the blackboards of our most eminent theoretical physicists. And it is an idea that has the potential to fundamentally reshape our understanding of our own cosmic place. The multiverse is not a single, coherent theory, but is a concept that arises in different forms from several of our deepest and most successful physical theories. The many worlds interpretation of quantum mechanics, as we have seen, suggests a constantly branching quantum multiverse, where every possible outcome of every quantum event is realized in a separate, parallel reality. The theory of eternal inflation suggests a bubble universe multiverse, where our own cosmos is just one, local, post-inflationary bubble in a much larger and eternally inflating meta-universe. And the landscape of string theory suggests a multiverse of different possible vacuum states, each with its own unique set of physical laws and constants. While the details of these different multiverse scenarios differ, they all share a common and deeply revolutionary idea that our universe is not the whole of reality. It is just one, small, and perhaps insignificant, part of a much larger and much more diverse cosmic tapestry. This is a vision that is both humbling and intellectually powerful. It is humbling because it represents the final and most profound step in the Copernican revolution, the long historical process of decentering humanity from a special and privileged position in the cosmos. We are not at the center of the solar system. We are not at the center of the galaxy, and we may not even be in the only universe. But the multiverse is also intellectually powerful because it provides a potential scientific explanation for one of the deepest and most puzzling features of our own universe. It's apparent and seemingly miraculous fine-tuning for the existence of life, the anthropic principle. In the context of a multiverse, becomes a simple and powerful selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. We could not have found ourselves anywhere else but the primary and most serious. Objection to the multiverse hypothesis is that it is, by its very nature, untestable. We can never, even in principle, travel to another bubble universe or communicate with a parallel quantum branch. The multiverse seems to lie forever beyond the reach of our direct empirical science. This has led many to argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful and perhaps the only naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. The LHC could provide hints of the multiverse in several different ways. The search for extra dimensions is, in a sense, a search for the multiverse. If the LHC were to discover evidence of extra dimensions through the production of microscopic black holes or the detection of missing energy, it would lend powerful circumstantial support to the brain world scenario, a specific and well-defined model of a multiverse. The properties of the Higgs boson itself could also provide a clue. As we have seen, the measured mass of the Higgs seems to place our universe in a metastable vacuum state. In the context of the string theory landscape, this is exactly what one might expect. The vast majority of the possible vacuum states in the landscape are not stable. And so, if universes are populated randomly across this landscape, we should not be surprised to find ourselves in a universe that is long-lived, but not eternally stable. The metastability of our vacuum could be a sign that we are living in a multiverse. The search for new and unexpected particles and forces at the LHC is also a search for the multiverse. If the LHC were to discover a new, long-lived particle or a new, very weak force, it could be a sign of a hidden, dark sector of particles that interacts with our own visible world only very weakly. And this dark sector could be the matter of a nearby parallel brain or a portal to a different hidden reality. The most direct and also most speculative way that the LHC could probe the multiverse is through the potential production of microscopic black holes. In some brain world models with large extra dimensions, the energy required to create a black hole is much lower than in our familiar four-dimensional spacetime. It is possible that the high-energy collisions at the LHC could have enough energy to create tiny, fleeting quantum black holes. These black holes would not be dangerous. They would evaporate almost instantly in a shower of Hawking radiation. But the specific properties of this radiation, its temperature, its spectrum, could provide us with a direct window into the physics of the extra dimensions, and perhaps even into the nature of quantum gravity itself. So far, the LHC has found no evidence for any of these exotic, multiverse-related phenomena. This has placed tight constraints on many of the simplest and most natural multiverse models, but the search is far from over. The upcoming high-luminosity upgrade of the LHC will increase its sensitivity to rare processes by a factor of 10, opening up a new and much wider window of discovery. And the next generation of even more powerful colliders, like the proposed Future Circular Collider, will push the energy frontier even further. The multiverse is an idea that is on the very edge of our scientific knowledge. It is a concept that is as beautiful and as profound as it is controversial and untestable. It may be that we will never find a definitive, smoking gun proof of its existence. But the search itself, the quest to understand whether our universe is the one and only, or just one of a vast and perhaps infinite cosmic ensemble, is a quest that is at the very heart of the human scientific adventure. It is a quest that is pushing our theories, our experiments, and our very imagination to their ultimate limits. The mysterious, invisible substance known as dark matter is one of the most profound and also most humbling puzzles in all of modern science. It is a substance that makes up about 85% of the total matter in the universe, and yet we have no idea what it is. It is the silent, gravitational scaffolding upon which the entire, visible structure of our cosmos is built. And yet, it remains completely and stubbornly invisible to all of our most powerful telescopes. The evidence for the existence of dark matter is overwhelming, and it comes from a host of different and independent astronomical observations. It was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of their visible stars alone. He concluded that there must be a huge amount of unseen, dark matter providing the extra gravitational glue. In the 1970s, the American astronomer Vera Rubin made the same startling discovery when she studied the rotation speeds of individual spiral galaxies. She found that the stars in the outer regions of these galaxies were orbiting far too quickly. According to Newton's laws of gravity, their speeds should have dropped off with distance from the galactic center, but they did not. They remained stubbornly high. The only way to explain this was to posit the existence of a vast and invisible halo of dark matter surrounding each galaxy, a halo whose gravitational pull was keeping the outer stars in their high-speed orbits. Since then, the evidence has continued to mount. The way that the gravity of massive galaxy clusters bends and distorts the light from more distant background galaxies, a phenomenon known as gravitational lensing, provides a direct way to map the distribution of mass, and it has confirmed the existence of these vast dark matter halos. The temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, also carry a clear and precise imprint of the amount of dark matter in the early universe. All of these different lines of evidence converge on a single and inescapable conclusion: the universe is filled with a new, and as yet undiscovered, form of matter. A matter that does not interact with light. A matter that is dark. But what is it the standard model of particle physics? our otherwise incredibly successful theory of the fundamental particles and forces, has no place for a dark matter particle. This means that dark matter must be something new, something that lies beyond our current and well-tested understanding of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a generic term for a new heavy particle that would interact with normal matter only through the weak nuclear force and gravity. This was an attractive idea for a number of reasons. Firstly, theories beyond the standard model, like supersymmetry, naturally predicted the existence of new, stable, and weakly interacting particles with just the right properties to be the dark matter. And secondly, a WIMP with a specific mass and interaction strength would have been produced in the hot early universe in just the right abundance to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and worldwide experimental search. But after decades of searching, in deep underground laboratories with satellite-based telescopes, and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a crisis in the field of dark matter physics, a crisis that has also been a period of immense creative ferment. Physicists are now exploring a whole host of new and more exotic dark matter candidates. Perhaps dark matter is not a WIMP, but an action, a hypothetical, ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Actions would be incredibly difficult to detect, as they interact with normal matter even more weakly than WIMPs, but a number of clever new experiments are being designed to search for their faint, telltale signature. Or perhaps dark matter is not a single particle, but is part of a whole, hidden dark sector. A complex world of dark particles and dark forces that interacts with our own visible world only through a faint, gravitational portal. The Large Hadron Collider is one of the most powerful tools we have in the search for dark matter. While it may not be able to detect a dark matter particle directly, as these particles would fly straight through the detectors without leaving a trace, it can search for them indirectly. If dark matter particles are produced in the high-energy collisions at the LHC, they will carry away energy and momentum. This would manifest in the detectors as missing energy, a clear and unambiguous imbalance in the energy of the visible particles that are produced in the collision. The search for this missing energy signature is one of the highest priorities of the LHC experimental program. So far, no such signal has been seen, which has placed tight constraints on many dark matter models. But the search continues. And with the upcoming high-luminosity upgrade of the LHC, the sensitivity to these kinds of signatures will be dramatically increased. A more radical and more controversial idea is that dark matter may not be a particle at all. Perhaps our understanding of gravity is wrong. The theory of modified Newtonian dynamics, or MOND, proposes that Newton's law of gravity needs to be modified at very low accelerations, like those found in the outer regions of galaxies. In this view, there is no dark matter. The observed anomalous rotation of galaxies is simply a sign that gravity is stronger than we thought in these regimes. While MOND has had some remarkable successes in explaining the rotation curves of individual galaxies, it has struggled to explain the observations of galaxy clusters and the cosmic microwave background without invoking some form of dark matter. The mystery of dark matter is not just a puzzle for particle physicists and astronomers. It is a profound philosophical challenge to our understanding of reality. It is a humbling reminder that the world we see, the world of stars, of planets, of light, is just a small, and perhaps insignificant, fraction of the true cosmic reality. We are living in a universe whose primary material constituent is completely unknown to us. But could the mystery of dark matter be connected to another, and even deeper, mystery, the existence of parallel universes? This is a speculative but deeply intriguing idea. In the brain world scenarios we have discussed, our universe is a three-dimensional membrane floating in a higher dimensional space. In some of these models, there could be other parallel branes nearby, and it is possible that the dark matter we observe is simply the gravitational influence of ordinary matter that is confined to one of these nearby shadow branes. We cannot see the matter on that other brane because light and the other standard model forces are trapped on it, but we can feel its gravity because gravity is a property of the entire higher dimensional bulk. In this view, dark matter is not a new, exotic particle. It is a ghost, a gravitational echo of a whole other universe that is existing just a hair's breadth away from our own. This is a breathtaking and almost poetic idea. It would mean that the invisible halo of dark matter that surrounds our own galaxy is not just a cloud of unknown particles. It is the gravitational shadow of a parallel, and perhaps even identical, Milky Way galaxy. A galaxy that is sharing our corner of the higher dimensional cosmos. The search for the nature of dark matter is one of the great scientific adventures of our time. It is a quest that is being pursued on multiple fronts, from the deep underground laboratories searching for a single, fleeting particle interaction, to the vast cosmological surveys mapping the large-scale structure of the universe, to the high-energy collisions at the Large Hadron Collider. The resolution of this mystery, whatever it may be, will undoubtedly mark a new and revolutionary chapter in our understanding of the universe, and it is a mystery that serves as a constant and powerful reminder of the vastness of our own ignorance and of the deep, dark, and beautiful secrets that are still waiting to be discovered in the silent, gravitational whispers of the cosmos. The Large Hadron Collider, in its first decade-long run, has been a story of both spectacular triumph and profound and puzzling silence. The triumph, of course, was the discovery of the Higgs boson in 2012, the final missing piece of the standard model of particle physics. A discovery that confirmed our understanding of the origin of mass and completed the beautiful and remarkably successful theoretical edifice that has been built over the last half-century. But the silence has been just as profound. In the years since the Higgs discovery, the LHC has been pushed to higher and higher energies and has collected an immense amount of data. And yet it has so far found no definitive evidence for any of the new physics beyond the standard model that was so confidently predicted by theorists. Supersymmetry, extra dimensions, microscopic black holes, new forces, new particles, all of the elegant and well-motivated. Theoretical solutions to the deep, remaining puzzles of the universe have, so far, failed to materialize. This has led to a period of deep soul-searching, of reevaluation, and also of immense creative excitement in the world of particle physics. We are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. The search for supersymmetry, or SUSY, has been one of the primary drivers of the LHC experimental program. The theory, as we have seen, is a beautiful and elegant one, and it has the potential to solve a number of the deep problems of the standard model at once, but the simplest and most natural. Versions of supersymmetry predicted that the superpartner particles should have masses that were within the reach of the LHC. The fact that we have not seen them is a major puzzle. This does not necessarily mean that supersymmetry is wrong. It could be that the superpartners are much heavier than we thought, and are simply beyond the reach of the current LHC. Or it could be that supersymmetry is a more complex and more hidden symmetry than our simplest models predicted. But the absence of any evidence for SUSY has forced physicists to consider other, and more unconventional, solutions to the hierarchy problem. The puzzle of the Higgs mass, another major, and so far fruitless. Search at the LHC has been the search for a particle candidate for dark matter. The WIMP paradigm, which was the leading theoretical framework for decades, has been severely constrained by the lack of any signal at the LHC and in the deep, underground direct detection experiments. This has led to a paradigm shift in the field of dark matter physics, a shift away from the simple, WIMP-centric view and towards a much broader and more diverse landscape of possibilities. The search is now on for actions, for sterile neutrinos, for dark photons, for a whole, hidden, dark sector of particles and forces. This is a much more challenging search, as these new candidates are often much lighter and interact even more weakly than WIMPs, making their signatures at the LHC much more subtle and difficult to detect. But it is a search that is being pursued with a new sense of creativity and urgency. The Higgs boson itself, while a monumental discovery, has also presented us with a new set of puzzles. Its measured properties are, so far, remarkably consistent with the predictions of the Standard Model. It seems to be a simple, garden-variety Higgs. But is this the whole story? Or is the Higgs boson a portal to a new and hidden sector of physics? Some theories suggest that there could be multiple types of Higgs bosons, a whole Higgs family. Others suggest that the Higgs boson could interact with new, as yet undiscovered, particles, like those of the dark matter sector. The precision study of the properties of the Higgs boson, its mass, its spin, its interactions with all the other known particles, is one of the primary goals of the ongoing LHC program. Any tiny deviation from the predictions of the Standard Model could be the first telltale sign of the new physics that we know must be there. To push the boundaries of this search, the LHC itself is undergoing a major and ambitious upgrade. The High Luminosity LHC, which is scheduled to begin operations in 2029, will not increase the energy of the collider, but will dramatically increase its luminosity, which is a measure of the number of particle collisions that occur per second. The HL-LHC will increase the luminosity by a factor of 10, allowing the experiments to collect a data set that is 10 times larger than the current one. This will be a game changer. It will allow physicists to study extremely rare processes that have never been seen before. It will allow for a much more precise measurement of the properties of the Higgs boson and of the other known particles, and it will dramatically increase the sensitivity of the search for new, high-mass particles and for the subtle, indirect signatures of new physics. The HL-LHC is a machine that is designed to search for the small cracks in the beautiful, but ultimately incomplete, edifice of the Standard Model. But what if the HL-LHC, too, finds nothing new? What if the universe is more subtle, more well-hidden, than even this powerful new machine can reveal? This is a possibility that the physics community is now beginning to seriously grapple with, and it has led to the planning of the next generation of even larger and more powerful particle colliders. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. Another complementary proposal is the International Linear Collider, a machine that would collide electrons and their antimatter counterparts, positrons, with incredible precision. A linear collider would not reach the same raw energies as a large circular proton collider like the FCC, but it would provide a much cleaner experimental environment, allowing for incredibly precise measurements of the properties of particles like the Higgs boson. The future of particle physics is at a crossroads. The easy, low-hanging fruit of the Standard Model has been picked. The path forward, into the deep and largely unknown territory beyond the Standard Model, is likely to be a long and challenging. 1. It will require a new generation of more powerful machines, a new level of global collaboration, and perhaps a new and more radical way of thinking about the fundamental nature of reality. But it is a journey that we must take. The mysteries of dark matter, of quantum gravity, of the origin of our own material existence are too deep, too profound, and too beautiful to be left unanswered. The LHC has opened a new window onto the universe, and what we have seen so far is just a glimpse of the vast and wonderfully mysterious landscape that still lies ahead. The Large Hadron Collider has already reshaped our understanding of the universe, but its next phase, the High Luminosity LHC, promises to push the boundaries of physics even further. Scheduled to become fully operational in 2029, this ambitious upgrade represents the next evolution in particle physics experimentation. This upgrade will not just increase the energy of the collisions, but will dramatically enhance the luminosity of the collider, a measure of the number of particle collisions that can be produced per second. The HL-LHC will increase the collision rate by a factor of 10, allowing the experiments to collect a data set that is 10 times larger than all the data collected in the first decade-long run of the LHC. This is a crucial step forward. In the world of high-energy physics, more data translates directly to more precision, and more precision translates to a greater chance of discovering new and subtle physical phenomena. Many of the processes that are predicted by theories beyond the Standard Model, such as the production of supersymmetric particles or the effects of extra dimensions, are expected to be extremely rare, occurring perhaps only once in every trillion collisions. To have any hope of observing these fleeting events, scientists need to create a truly astronomical number of collisions. The HL-LHC is a machine that is designed to do exactly that. It is a rare process factory, a powerful tool designed to search for the proverbial needle in a cosmic haystack. One of the primary scientific goals of the HL-LHC is to study the Higgs boson with unprecedented precision. The discovery of the Higgs in 2012 was a monumental achievement, but it was just the beginning of the story. We know that the Higgs boson exists, but we still know very little about its true nature. Is it a single, fundamental particle, as the Standard Model predicts, or is it a composite object made of other, more fundamental constituents? Is it part of a larger, more complex Higgs sector with other, as yet undiscovered, Higgs-like particles? The HL-LHC will allow physicists to measure the properties of the Higgs, its mass, its spin, its interactions with all the other known particles, with a precision that is an order of magnitude better than what is currently possible. Any tiny deviation from the predictions of the Standard Model would be a smoking gun signal of new physics, a window into the reality that lies beyond our current understanding. The HL-LHC will also dramatically increase our sensitivity to the search for new, high-mass particles. If theories like supersymmetry are correct, but the new superpartner particles are simply too heavy to have been produced in significant numbers at the current LHC. The huge increase in the number of collisions at the HL-LHC will give us a much better chance of seeing them. The search for the elusive dark matter particle will also be a major focus of the HL-LHC program. The upgraded collider will be able to search for a much wider range of dark matter candidates, and with much greater sensitivity than the current LHC. The search for the missing energy signature of dark matter production will be pushed to new limits, and new, more subtle. Search strategies will be employed to try and catch a glimpse of this invisible, and mysterious component of our universe. The technological challenges of upgrading the LHC to its high luminosity configuration are immense. It is a project that is pushing the very limits of modern accelerator and detector technology. It requires the development of new, more powerful, and more compact superconducting magnets to focus the proton beams down to an even smaller size at the collision points. It requires a new generation of crab cavities, a special kind of radio frequency cavity that can tilt the proton bunches just before they collide to maximize their overlap and the collision rate. And it requires a complete and ambitious upgrade of the giant detectors, Atlas and CMS. These detectors will need to be equipped with new, more granular, and more radiation-resistant sensors that can handle the incredible and unprecedented data rates of the HL-LHC. This is a monumental engineering endeavor, an endeavor that is requiring a new level of innovation, of ingenuity, and of global scientific collaboration. But the potential scientific payoff is enormous. The HL-LHC will be one of the most important scientific projects of the coming decades. A machine that has the potential to rewrite the laws of physics and to answer some of the most fundamental questions about the nature of our universe. It may be the machine that finally discovers the dark matter particle, that finds the first evidence of supersymmetry, that reveals the existence of extra dimensions, or that uncovers a whole new and completely unexpected layer of physical reality. But even if the HL-LHC finds nothing new, even if the standard model continues to hold up to every new and more precise test, that in itself would be a profound and deeply puzzling result. It would mean that the solutions to the deep problems of the standard model lie at an energy scale that is far beyond the reach of any conceivable future accelerator. It would mean that we may need a completely new and more radical theoretical paradigm to make progress. It might even mean that we are beginning to approach a fundamental limit to our ability to probe the universe with our current reductionist methods. The HL-LHC is a bet, a bold and ambitious bet on the future of particle physics. It is a bet that the universe still has new and discoverable secrets to reveal at the energy scale that we can access. And it is a bet that the human quest for knowledge, for a deeper understanding of our cosmic home, is a journey that is still far from over. The discoveries that are made at the HL-LHC in the coming decades will undoubtedly reshape our understanding of the universe in ways that we cannot yet imagine, and will set the course for the next generation of scientific exploration. The quest to understand the fundamental nature of reality is a journey that will not end with the Large Hadron Collider, or even with its high luminosity upgrade. The human spirit of discovery is a relentless one, and physicists are already dreaming of and planning for the next generation of even larger and more powerful scientific instruments, machines that will be able to push the frontiers of our knowledge to new and currently unimaginable energy scales. One of the most ambitious of these proposals is the Future Circular Collider, a project that is currently being studied at CERN. The FCC would be a true scientific behemoth, a 100-kilometer-long underground ring, almost 4 times the size of the current LHC. Such a machine would be capable of reaching collision energies that are about 7 times higher than the LHC, opening up a vast and largely unexplored new territory for discovery. The FCC is envisioned as a multi-stage project. The first stage would be an electron-positron collider, a Higgs factory that would be able to produce millions of Higgs bosons in a very clean and well-understood experimental environment. This would allow for incredibly precise measurements of the properties of the Higgs, a search for any tiny deviation from the predictions of the standard model that could signal the existence of new physics. The second stage would be a high-energy proton-proton collider, a true discovery machine that would be able to directly search for new heavy particles up to an energy scale that is far beyond the reach of the LHC. If supersymmetry or extra dimensions or a new heavy force of nature exists, the FCC would be our best hope of finding it. Another and complementary proposal is the International Linear Collider, a project that is being championed by a global collaboration of scientists. The ILC would not be a circular machine, but a linear one, about 30 kilometers long, that would collide electrons and positrons with very high precision. A linear collider cannot reach the same raw energies as a large, circular proton collider like the FCC, but it has a key advantage: the collisions are much cleaner. When protons, which are composite objects made of quarks and gluons, collide, they create a very messy and complex spray of particles, an electron-positron collision. On the other hand is a much simpler and more well-defined interaction, which allows for incredibly precise measurements of the properties of the particles that are produced. The ILC would be a powerful precision tool for studying the Higgs boson and for searching for the subtle, indirect signatures of new physics. But the future of fundamental physics is not just about building bigger and bigger colliders. It is also about exploring new and more innovative ways to probe the secrets of the universe. The growing field of astroparticle physics is a beautiful example of this. It is a field that uses the universe itself as a laboratory. High-energy cosmic rays, neutrinos, gamma rays, gravitational waves. These are the particles that are produced in the most extreme and energetic environments in the cosmos. In supernovae, in neutron star collisions, in the hearts of active galaxies. By studying these cosmic messengers with a new generation of powerful ground-based and space-based detectors, we can probe the laws of physics at energies and in conditions that are far beyond the reach of any terrestrial accelerator. The search for the nature of dark matter is a prime example of this synergistic approach. While the LHC is searching for the production of dark matter particles in high-energy collisions, a host of other experiments are searching for them in different ways. Deep, underground detectors are trying to catch the rare, fleeting signal of a dark matter particle from our galaxy's halo bouncing off an atomic nucleus. Telescopes are searching for the faint, gamma-ray glow of dark matter particles annihilating each other in the dense center of our galaxy. And cosmological surveys are mapping the distribution of dark matter on the largest scales, providing crucial clues to its properties and its history. The quest to unify gravity and quantum mechanics is another area where a multi-pronged approach is essential. While a future, high-energy collider may one day find the first direct evidence of new quantum gravitational physics, our best hope for probing this realm in the near future may come from the precision study of the cosmos itself. The search for the faint, primordial signature of gravitational waves from the period of cosmic inflation in the cosmic microwave background is a direct window into the physics of the very early and very high-energy universe, and the study of black holes, both with electromagnetic telescopes and with gravitational wave detectors, is providing us with a unique and powerful laboratory for testing the predictions of general relativity in the strong field regime, the very place where we expect the first subtle signs of its breakdown to appear. And finally, the future of fundamental physics will be increasingly intertwined with the development of new and more powerful computational tools. The vast amounts of data that will be generated by the next generation of experiments will require a new level of computational power and a new generation of sophisticated, AI-driven algorithms to analyze. And the development of practical, large-scale quantum computers could, one day, revolutionize the field of theoretical physics, allowing us to perform simulations of complex quantum systems, like the dynamics of a quark-gluon plasma or the quantum geometry of spacetime itself. that are completely intractable on a classical computer. The future of our quest to understand the universe is a bright and incredibly exciting one. It is a future that will be driven by a rich and diverse ecosystem of different and complementary experimental and theoretical approaches. It is a future that will require a new level of global collaboration, of long-term vision, of scientific creativity. And it is a future that holds the promise of answering some of the deepest, most profound, and most beautiful questions that humanity has ever asked. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes, is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that pushes the very limits of our imagination, and also of our scientific methodology. If these other universes exist, they are, by their very nature, likely to be forever beyond the reach of our direct observation and experimentation. And so, the question arises if the multiverse is a theory that can never be proven. What does that mean for the future of physics? Does it signal a fundamental limit to our ability to understand the cosmos, or does it require us to adopt a new and more philosophical understanding of what constitutes a scientific theory? The multiverse is not a single, speculative idea that has been pulled out of thin air. It is a concept that arises naturally and almost inevitably from several of our best and most well-tested physical theories. The many worlds interpretation of quantum mechanics, the theory of eternal cosmic inflation, the landscape of string theory, all of these different and well-developed theoretical frameworks seem to point towards the same radical conclusion that our universe is not the one and only. This is a powerful and deeply compelling convergence of ideas. When multiple independent lines of theoretical inquiry all point towards the same surprising conclusion, it is a sign that we should take that conclusion seriously, even if it is a conclusion that challenges our most basic common sense intuitions, but the untestable and perhaps unfalsifiable nature of the multiverse remains a profound and deeply problematic challenge. Science, in its standard form, is a discipline that is based on empirical evidence. A theory is considered scientific to the extent that it makes testable and falsifiable predictions. The multiverse, in its grandest conception, seems to fail this test. This has led to a deep and often contentious debate within the physics and philosophy of science communities. Some argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful, and perhaps the only, naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. But what if no evidence, either direct or indirect, for the multiverse is ever found? What if, after decades of searching, the cosmic microwave background remains stubbornly smooth? The LHC finds no sign of extra dimensions or microscopic black holes. and the fundamental constants of nature continue to appear as single, unexplained numbers. This would not necessarily mean that the multiverse does not exist. It could simply mean that its effects are too subtle, too well hidden for our current, and even our future, experiments to detect. But it would undoubtedly lead to a period of deep crisis and reevaluation in theoretical physics. It would force us to confront the possibility that we may have reached a fundamental limit to our ability to probe the ultimate nature of reality. It would force us to ask a difficult and deeply uncomfortable question: what if the universe is just the way it is, and there is no deeper reason why? This is a possibility that many scientists are reluctant to accept. The entire history of science has been a history of finding deeper and more unified explanations for the phenomena of the natural world. To accept that the fundamental properties of our universe are just a random, accidental set of numbers with no underlying logical or physical explanation seems like a betrayal of the very spirit of the scientific enterprise. It would be a return to a kind of pre-scientific, magical thinking where the world is just a collection of unexplained, brute facts. This is why the search for a final bootstrap theory, a theory of everything that would uniquely and necessarily determine all the properties of our universe, remains such a powerful and enduring dream. But what if this dream is also an illusion? What if the universe is not a unique mathematical necessity, but is in fact just one of a vast and perhaps infinite number of possibilities? The absence of any evidence for the multiverse would not prove that it does not exist, but it would perhaps force us to adopt a new and more humble stance towards our own scientific knowledge. It would force us to accept that there may be certain fundamental questions about the ultimate nature of reality that are, in principle, unanswerable. It would force us to embrace a kind of learned ignorance, a recognition that the universe is not a puzzle to be solved, but a mystery to be lived. The debate over the multiverse is not just a debate about the nature of the cosmos. It is also a debate about the nature of science itself. It is a debate about the limits of our knowledge, about the role of evidence, of theory, of philosophy, of aesthetics, in our quest to understand the universe. And it is a debate that is likely to continue for a long time to come. But whatever the ultimate outcome, the very fact that we are able to have this debate, that we are able to conceive of realities that are so far beyond our own direct experience, is a testament to the remarkable and perhaps even cosmic power of the human mind. The search for the multiverse, whether it ultimately succeeds or fails, is a search that is pushing us to be better scientists, better philosophers, and perhaps even better and more humble human beings. The Large Hadron Collider, in its relentless and powerful probing of the subatomic world, has been a story of both profound discovery and of deep and deepening mystery. The discovery of the Higgs boson in 2012 was a triumph of human ingenuity, a beautiful confirmation of the standard model of particle physics, and a moment that seemed to bring us to the very threshold of a complete understanding of the known, visible universe. But in the years since, the LHC has also given us a profound and puzzling silence. The new physics that was so confidently expected to lie just around the corner, the elegant symmetry of supersymmetry, the strange geometry of extra dimensions, the ghostly particles of dark matter has, so far, failed to appear. This has led some to wonder if we are approaching the end of physics, a point where our current collider-based methodology has reached its fundamental limits. But this is a deeply pessimistic and likely incorrect view. The absence of new discoveries at the LHC is not a sign that there is no new physics to be found. It is a sign that the new physics is more subtle, more well hidden, and perhaps more strange. than our simplest and most natural theories predicted. The universe is not a puzzle that gives up its secrets easily, and the quest to understand it is a long and often winding journey. A journey that is full of both exciting breakthroughs and long periods of patient and often frustrating exploration. The Higgs boson itself, while confirming the Standard Model, has also opened up a new and largely unexplored landscape of questions. Is it a fundamental, point-like particle, or is it a composite object made of other, more fundamental constituents? Is it the only Higgs boson, or is it part of a larger, more complex Higgs sector? Does it interact with the mysterious dark sector of the universe? The detailed, precision study of the properties of the Higgs boson is one of the primary goals of the ongoing LHC program and of its upcoming high-luminosity upgrade. Any tiny deviation from the predictions of the Standard Model could be the first telltale sign of the new physics that we know must be there. The mystery of dark matter remains one of the greatest and most humbling challenges in all of science. The failure to find a WIMP particle at the LHC and in the direct detection experiments has forced the field to cast a much wider net, to explore a whole new zoo of more exotic and more difficult to detect dark matter candidates. This is a search that will require a new generation of more sensitive experiments and a new level of creativity and ingenuity from both theorists and experimentalists. And the ultimate mystery, the unification of gravity with quantum mechanics, is a challenge that will likely require a new and more powerful generation of particle accelerators, machines like the proposed Future Circular Collider that can probe the energy scales where the effects of quantum gravity are expected to become apparent. But the future of fundamental physics is not just about building bigger and bigger machines. It is also about exploring new and more complementary avenues of inquiry. The growing field of astroparticle physics, which uses the universe itself as a laboratory, is providing a new and powerful window onto the fundamental laws of nature. The precision study of the cosmic microwave background, the detection of gravitational waves, the search for high-energy neutrinos from distant astrophysical sources, all of these are providing crucial and often unique clues to the physics that lies beyond our current understanding. The story of our universe, as revealed by the LHC and by all our other scientific explorations, is a story that is still being written. We have learned an immense amount in the last century, but we have also learned the true and vast extent of our own ignorance. We have discovered that the universe we see, the universe of atoms, of stars, of galaxies, is just a tiny 5% fraction of the true cosmic reality. The rest is a dark and largely unknown world of dark matter and dark energy. We have discovered that our universe may have been born from a mysterious and perhaps eternal multiverse. We have discovered that the very fabric of our reality, the space and the time that we inhabit, may be a fragile and perhaps even temporary illusion. These are discoveries that should not lead us to a sense of intellectual despair, but to a feeling of profound and beautiful humility. They are a reminder that we are not the masters of the universe, but are just a small and very young species, just beginning to wake up to the true and breathtaking scale and strangeness of our cosmic home. The quest for knowledge is a long and perhaps infinite one, and the Large Hadron Collider, for all its power and its glory, is just one small step on this grand and unending human adventure, the greatest discoveries, the most profound revelations. The answers to the deepest questions that humanity has ever asked may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world. The Large Hadron Collider is more than just a powerful machine. It is a symbol of our species' insatiable curiosity, a testament to our relentless drive to understand the fundamental nature of the universe. It is a modern-day cathedral, a place where thousands of scientists from all over the world come together to ask the biggest and most profound questions. And while the LHC has already delivered one of the greatest scientific triumphs of our time, the discovery of the Higgs boson, its work is far from over. The search for answers to the deep, remaining mysteries of the cosmos continues. And the LHC, with its ongoing upgrades and its ever-increasing power, remains at the very forefront of this grand human endeavor. The mystery of dark matter is one of the primary targets of the ongoing LHC program. While the simplest WIMP candidates have not been found, the search has now expanded to a much wider and more diverse range of possibilities. The LHC is searching for the signatures of action-like particles, for the production of sterile neutrinos, for the subtle and often hidden signals of a whole new dark sector of particles and forces. This is a challenging and painstaking search, a process of sifting through a mountain of data for a tiny and often ambiguous signal. But it is a search that is driven by the profound realization that the vast majority of the matter in our universe is still completely unknown to us. The puzzle of the matter-antimatter asymmetry is another and equally profound mystery that the LHC is uniquely positioned to address. The LHC-B experiment, one of the 4 large detectors at the LHC, is specifically designed to study the subtle differences in the behavior of matter and antimatter by precisely measuring the decays of particles that contain beauty quarks. Any tiny deviation from the predictions of the standard model in these decays could be the first crucial clue to the new source of CP violation that is needed to explain our own matter-dominated existence. The search for extra hidden dimensions of space is another, and more speculative, but also more exciting, avenue of research at the LHC. The detection of microscopic black holes, or of a tower of heavy Kaluza-Klein particles, would be a discovery of revolutionary and almost unimaginable significance. It would prove that our familiar 4-dimensional reality is just a small slice of a much larger and much more complex multidimensional cosmos, and it would open up a whole new and previously hidden landscape for scientific exploration. The possibility of a multiverse is perhaps the most mind-bending, and also most controversial, of all the ideas that the LHC is capable of probing. While a direct detection of another universe is impossible, the LHC could provide crucial indirect evidence. A discovery of supersymmetry, or of extra dimensions, would lend powerful circumstantial support to the string theory landscape and the brane world scenarios, both of which naturally lead to the idea of a multiverse. And the precision measurement of the properties of the Higgs boson could tell us whether our own universe's vacuum is stable or metastable, a clue that could point towards our place in a larger cosmic ensemble of different possible vacuum states. The quest for new physics at the LHC is a quest that is being pushed to new limits by the ambitious and technically challenging high-luminosity LHC upgrade. This is a project that will transform the LHC into an even more powerful discovery machine, a machine that will be able to produce a dataset that is 10 times larger than anything we have collected so far. This huge increase in luminosity, in the number of collisions, will allow physicists to search for extremely rare processes that are simply inaccessible at the current LHC. It will be like turning up the brightness on our picture of the subatomic world, allowing us to see the faint and subtle details that have so far been hidden in the noise. The LHC will be a Higgs factory, producing millions of Higgs bosons and allowing for an incredibly precise measurement of their properties. It will be a dark matter hunter, with a much greater sensitivity to a wide range of dark matter candidates. And it will be a new physics explorer, with the potential to discover new particles, new forces, and new symmetries of nature that could revolutionize our understanding of the universe. But the future of particle physics does not end with the HL-LHC. The global scientific community is already planning for the post-LHC era, for the next generation of even larger and more powerful particle accelerators that will be needed to push the energy frontier even further. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. The Compact Linear Collider is another. These are machines that will not be built for decades, but they are a testament to the long-term vision, the ambition, and the enduring curiosity of the human spirit. The search for the fundamental truths of the universe is a long and often difficult journey. It is a journey that is full of both exciting breakthroughs and long periods of patient and sometimes frustrating exploration. And it is a journey that requires a deep and unwavering commitment to the power of science, of reason, of collaboration, to unravel the deep and beautiful secrets of the cosmos. The Large Hadron Collider and the machines that will come after it are more than just scientific instruments. They are symbols of our species' highest aspirations. They are the modern-day pyramids, the cathedrals of our time, monuments to our collective desire to understand our place in the universe, to ask the biggest questions, and to dare to seek the answers. The journey is far from over. The greatest mysteries, the most profound discoveries, the answers to the questions that have haunted humanity since the dawn of consciousness may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world.